Hello there, and welcome to Life Beyond Seen, a quiet place where big ideas are allowed to slow down, where science doesn't hurry you along, and where curiosity is invited to sit comfortably for a while. This is a space for listening rather than skimming, for letting thoughts unfold gently instead of demanding answers right away. Tonight, we're going to spend some time with a story that is vast, unsettling, and strangely intimate. Even though it happened long before humans ever walked the earth, it's a story about the ocean, not as we know it today, but as it once was when something essential slipped away. Not all at once, not dramatically, but slowly enough that life barely noticed, until it was too late. Imagine the ocean as it usually appears in your mind, wide, restless, endlessly moving. Waves stacking and collapsing, currents looping across the planet, surface waters glittering under sunlight while the deep remains dark and cold. It feels permanent, reliable, something that has always been there and always will be. Even when storms tear across it or ice locks parts of it away, the ocean still feels alive, breathing in its own way, circulating energy, feeding entire worlds. We tend to think of it as resilient by default, too large to fail, too ancient to be fragile. But there was a time when that assumption was very wrong. Tonight's story begins not with a sudden catastrophe, not with an explosion or an impact from the sky, but with a quiet change in balance, a warming here, a slowdown there, a shift so gradual that it didn't announce itself with noise or flame. Instead, it crept through the water, layer by layer, until the ocean itself began to suffocate. Scientists call this kind of episode an anoxic event, a period when oxygen vanished from vast stretches of the sea. But that technical phrase doesn't quite capture what it means. It wasn't just that oxygen levels dropped. It was that the ocean, for a long time, nearly lost its ability to support complex life at all. Before we go any further, take a moment to notice where you are right now. Maybe you're listening late at night, lights dimmed, the world quiet except for the soft background sounds that come with being awake when most things have settled down. Or maybe it's daytime for you, and this is a pause between tasks, something to focus on while the rest of the day hums along in the background. Wherever you are, think about the nearest body of water you've ever stood beside, a shoreline, a river, a lake, or the open sea. Think about how it smelled, how it moved, how it felt to look out over something that didn't seem to end. That sense of depth, of hidden layers beneath the surface, is exactly where this story lives. If you find this kind of slow exploration calming or interesting, or if it helps you unwind and settle your thoughts, you're very welcome to like the video or subscribe to the channel. It helps this quiet corner reach others who might be looking for the same kind of unhurried curiosity. There's no rush though. Nothing here needs to be optimized or skimmed. We're just moving forward at a steady, comfortable pace. Now, when people hear that the ocean nearly died, the mind often jumps to images of empty waters, floating debris, or sudden mass extinctions. But the reality was stranger and more subtle than that. Life didn't vanish overnight. Fish didn't suddenly wash up everywhere. Instead, the ocean became layered in a way that changed everything. The surface might still have looked alive, at least for a while. Sunlight still reached the upper waters. Photosynthetic organisms still did what they had always done. But below that thin, active skin, something fundamental was breaking down. Oxygen is easy to take for granted because we live immersed in it. We breathe without thinking about it. We assume that life simply requires it, and that it will always be there. But oxygen in the ocean is not guaranteed. It is delivered, mixed, and maintained through a delicate combination of temperature, circulation, biology, and chemistry. When any one of those slips out of balance, oxygen can disappear far faster than it returns. During anoxic events, entire regions of the ocean became depleted, sometimes down to levels where most animals could no longer survive. This wasn't the first time oxygen had ever been scarce in Earth's oceans. Early life evolved in a world with little to no oxygen at all. But by the time these events occurred, the ocean had already become rich with complex ecosystems. Creatures had evolved bodies, behaviours, and food webs that depended on oxygen being present. Remove it, and the system doesn't just adjust, it unravels. What makes this story especially unsettling is that the trigger wasn't a single dramatic cause. It was a cascade. Warmer global temperatures reduced the mixing of ocean waters. When surface waters warm, they become lighter and less likely to sink. That sinking motion is one of the main ways oxygen from the atmosphere gets carried into the deep ocean. As mixing slowed, deeper waters became isolated. At the same time, nutrients flooded the seas, fueling massive blooms of microscopic life near the surface. When those organisms died, they sank, and bacteria feeding on them consumed even more oxygen below. The ocean was being starved from above and drained from within. This process didn't need violence to be devastating, it just needed time. As oxygen levels dropped, certain microbes thrived. Some of them produced hydrogen sulfide, a toxic gas that smells like rotten eggs, and is lethal to most complex life. In places where oxygen was completely absent, these bacteria took over, changing the chemistry of the water itself. Entire zones became hostile, not just low in oxygen, but actively poisonous. Anything that couldn't escape upward or away simply vanished from the record. Yet even then, the ocean didn't become empty. It changed. Life reorganized itself around what was left. Simple organisms adapted. Some found refuge in narrow bands of water where oxygen still lingered. Others evolved metabolisms that didn't require oxygen at all. The ocean didn't die in the way we imagine death. It entered a state of prolonged crisis, one where complexity was stripped away, and survival favoured the few that could tolerate extreme conditions. Geologists didn't learn about these events by finding piles of dead fish or obvious markers of catastrophe. They found them written quietly in stone. Layers of dark, organic-rich sediment known as black shales began appearing in the geological record. These rocks formed when large amounts of organic matter sank to the seafloor and were preserved instead of decomposed, because there was little oxygen to break them down. Each layer is like a page torn from an ancient ocean's diary, recording long stretches of breathless water. What's remarkable is how widespread these layers are. They aren't confined to one basin or one coastline. They appear across continents, suggesting that entire ocean systems were affected at once. This wasn't a local problem, it was global, and it happened more than once. One of the most severe of these episodes occurred during the Mesozoic era, when dinosaurs roamed on land and the seas were filled with unfamiliar creatures. The planet was warmer than it is today. Sea levels were higher. Continental positions shaped ocean circulation in ways very different from now. These conditions made the system vulnerable. Once it tipped, it stayed altered for an extraordinarily long time. For life living through it, there was no awareness of an event. There was just a shrinking of habitable space, a loss of familiar species, a dominance of organisms that most ecosystems usually keep in check. From a human perspective, it's tempting to see these changes as dramatic turning points, but from within the ocean, they would have felt like a slow narrowing of options. As we continue, we'll move deeper into how these conditions developed, what exactly happened beneath the surface, and how scientists pieced together a story from chemical fingerprints and fossil absences. We'll look at which creatures disappeared, which ones endured, and how long recovery actually took. Not a neat rebound, not a return to the previous world, but a gradual rebuilding into something different. For now, let this first stretch settle in. The idea that even something as vast as the ocean depends on balance, that it can lose something as basic as oxygen without fanfare. That collapse doesn't always announce itself loudly. Sometimes it arrives quietly, carried on warm currents and slow circulation, changing everything while still looking, from the surface, almost the same. And from here, as the conditions that led to this crisis come into clearer focus, the story naturally widens because once the ocean begins to lose its breath, nothing else on the planet remains unaffected for long. The ocean has always been noisy in ways we rarely think about. Even before whales sang and shrimp snapped, long before humans listened with instruments and charts, the sea was full of motion, exchange, and constant interaction. Water moving against water, particles drifting, organisms feeding, growing, dying, and becoming food for something else. Sound is only one expression of that activity. The real noise of the ocean is chemical and biological, an ongoing conversation carried by currents, nutrients, and oxygen. When scientists say the ocean nearly went silent, they don't mean it literally lost sound. They mean that much of this constant exchange slowed, thinned, and in some places stopped altogether. To understand how that could happen, it helps to picture the ocean not as a single uniform body of water, but as a layered system with very different conditions stacked on top of one another. At the surface, sunlight drives photosynthesis. Microscopic organisms convert light and carbon dioxide into energy, forming the base of most marine food webs. Below that, in darker waters, life depends on what sinks from above. Dead cells, waste, fragments of organic matter drift downward, feeding bacteria and animals adapted to low light and colder temperatures. And beneath even that, in the deepest layers, life slows further, existing on thin margins where energy is scarce, and oxygen delivery depends entirely on circulation from the surface. In a healthy ocean, these layers are connected. Wind, temperature differences, and Earth's rotation drive large-scale currents that mix water vertically and horizontally. Cold, dense water sinks at high latitudes and travels through the deep ocean, carrying oxygen with it. Warmer water rises elsewhere, releasing nutrients back toward the surface. This slow overturning acts like the ocean's breathing system. It doesn't inhale and exhale quickly, but over centuries and millennia, it keeps oxygen moving and ecosystems stable. During the periods we're talking about that breathing weakened, as global temperatures rose, surface waters warmed. Warm water is lighter than cold water, which means it resists sinking. The more pronounced the temperature difference between surface and deep water, the harder it becomes for the ocean to mix vertically. This led to stronger stratification, with warm, oxygen-rich water sitting on top and cooler, increasingly stagnant water trapped below. At first, this didn't seem catastrophic. The surface ocean could still support life. Sunlight was still there. Photosynthesis continued. But the deep ocean began to change in ways that weren't immediately visible. Without regular replenishment, oxygen levels in deeper waters slowly declined. Animals that lived there had evolved to survive on relatively low oxygen already, but there are limits. As levels dropped further, sensitive species disappeared. Burrowing organisms that normally churned sediment and helped circulate oxygen into the seafloor vanished, which made conditions even worse. This loss of activity reduced one of the ocean's many small stabilizing feedbacks, further encouraging stagnation. At the same time, more nutrients were entering the ocean. Volcanic activity, continental weathering, and changing rainfall patterns delivered phosphorus and nitrogen into coastal and open waters. These nutrients fueled large blooms of plankton near the surface. For a while, this might have looked like abundance. More microscopic life means more food for larger organisms, at least initially. But this abundance came with a hidden cost. When these blooms collapsed, as they always do, enormous amounts of organic material sank into deeper layers. Bacteria feeding on this material consumed oxygen in the process. In a well-mixed ocean, this oxygen would be replaced. In a stratified ocean, it wasn't. Oxygen consumption outpaced oxygen delivery, pushing large regions into hypoxia and eventually into full anoxia, where oxygen was effectively absent. Once anoxia set in, the chemistry of the water shifted dramatically. Microorganisms that normally remain in the background became dominant. Sulfate-reducing bacteria, which do not require oxygen, thrived in these conditions. Their metabolism produces hydrogen sulfide as a waste product. Hydrogen sulfide is toxic to most multicellular life and reacts with metals in the water and sediment, leaving distinctive chemical signatures that scientists can detect millions of years later. These chemical changes didn't stay neatly contained at depth. In some cases, anoxic waters expanded upward, squeezing oxygenated zones into thinner and thinner layers near the surface. Life was compressed into narrow habitable bands, with hostile conditions above and below. Any disruption, a change in temperature, a shift in circulation, could collapse these refugees entirely. From a distance, the ocean might still have looked blue. Its surface would still reflect the sky. Waves would still break. But functionally, it was becoming quieter. Fewer interactions, shorter food chains, less diversity. Complexity was being stripped away, not by a single blow, but by sustained stress that favoured only the most tolerant organisms. Fossil records from these intervals show this pattern clearly. Groups that had thrived for millions of years vanished or were reduced to remnants. Reef systems collapsed. Predatory species declined as their prey disappeared. In some regions, entire categories of animals are simply missing from the record for long stretches of time, not because fossils failed to form, but because the organisms themselves were gone. Meanwhile, microbes flourished. Bacteria and archaea adapted to low oxygen and no oxygen conditions expanded their reach. The ocean became more chemically active, but biologically simpler. Energy still flowed, but it cycled through fewer hands, so to speak. Instead of moving through complex webs of animals, it was processed repeatedly by microorganisms. This shift had consequences beyond the ocean itself. Anoxic waters can release gases into the atmosphere, including hydrogen sulfide and methane. In extreme cases, these gases may have reached the surface and entered the air, stressing terrestrial ecosystems as well. There is evidence suggesting that some anoxic events coincided with disruptions on land, including plant die-offs and changes in climate patterns. What's striking is how long these conditions persisted. We're not talking about decades or even centuries. Some anoxic events lasted hundreds of thousands to millions of years. Entire evolutionary paths were closed off for unimaginably long spans of time. Recovery, when it came, was slow and uneven, requiring shifts in climate, circulation and nutrient balance before oxygen could once again penetrate the deep ocean consistently. During these long intervals, the ocean wasn't static. It continued to change, pulse and reorganize, but it did so within narrow constraints. The dynamic, richly layered system we're familiar with today was replaced by something flatter and more monotonous. Fewer niches, fewer surprises, less room for experimentation. This is what is meant by silence in this context. Not the absence of water or motion, but the loss of complexity. The quieting of interactions that normally keep ecosystems resilient. The dominance of processes that run on minimal requirements, leaving little space for diversity to return. As scientists began to recognize these patterns in the geological record, they realized that anoxic events weren't rare anomalies. They were recurring features of Earth's history, emerging under specific conditions. Warm climates, high nutrient input, restricted circulation. When these factors aligned, the ocean became vulnerable. This realization changed how researchers thought about marine extinction and recovery. It wasn't always about sudden disasters. Sometimes it was about thresholds. Push the system far enough in one direction and it doesn't bounce back easily. It settles into a new state that can persist for a very long time. From here, the story naturally turns toward a closer look at what it actually means for an ocean to lose oxygen on such a scale, and why oxygen, despite being so abundant in our atmosphere, is such a fragile component of marine life. Because once you start tracing how oxygen moves through water, how it's consumed, and how easily that balance can be disrupted, The idea of a blue world going quiet begins to feel less distant and more like a lesson written very carefully and very slowly into the history of the planet. When we talk about an ocean dying, it's easy to imagine a dramatic moment, a line crossed, a before and an after. Something alive becomes something dead, and the change is obvious. But oceans don't die in that way. They don't stop moving, they don't vanish. Water continues to circulate, waves still form, and tides still rise and fall. What changes is not the presence of the ocean, but its function. An ocean can remain physically present while losing many of the qualities that make it a living system. To understand what that means, it helps to step away from the idea of life and death as binary states. In biological systems, especially ones as large as oceans, there are gradients. There are degrees of vitality, levels of complexity, and layers of interaction that can be lost one by one. An ocean doesn't go from healthy to dead overnight. It sheds diversity. It simplifies. It becomes less capable of supporting the kinds of life that once thrived there. Life in the ocean is built around oxygen, not because oxygen is the only way to generate energy, but because it is an efficient one. Oxygen allows organisms to extract more energy from food, supporting larger bodies, active movement, and complex behaviours. Fish, mollusks, crustaceans, marine reptiles, and many planktonic animals all rely on oxygen to sustain their metabolisms. Remove oxygen, and these organisms don't adapt easily. Their physiology is tuned to a world where oxygen's available, even if only in small amounts. When oxygen levels begin to fall, the first changes are subtle. Animals alter their behaviour. They move into shallower water or migrate laterally, tracking narrow zones where oxygen is still present. Some reduce activity to conserve energy. Reproduction slows. Growth rates drop. These changes don't leave obvious marks in the fossil record right away, but they weaken populations over time. As oxygen declines further, these strategies stop working. There simply isn't enough energy available to sustain complex bodies. Sensitive species disappear first. Predators often follow soon after, because their prey becomes scarce. What remains are organisms that either require very little oxygen or none at all. This shift marks a fundamental change in how the ocean operates. At this point, the ocean isn't empty, but it's profoundly altered. Microbial life dominates. Bacteria and archaea capable of anaerobic metabolism take over large portions of the system. These organisms don't build shells or skeletons. They don't leave dramatic fossils. Their world is chemical rather than physical, driven by electron transfers and metabolic pathways that don't involve oxygen. This microbial dominance has cascading effects. Without animals stirring sediments, the seafloor becomes more stable and less mixed. Nutrients are recycled differently. Certain chemical compounds accumulate that would normally be consumed or transformed by oxygen-dependent processes. The entire system settles into a new equilibrium, one that is harder to disrupt but also far less diverse. Calling this state dead is misleading if taken literally. Life continues, sometimes in great abundance, but it is a different kind of life, one that lacks the structural complexity we associate with healthy ecosystems. Coral reefs cannot form without oxygen-rich water. Large predators cannot persist. Long food chains collapse into short loops dominated by microbes. From a functional perspective, the ocean loses resilience. In a diverse system, disturbances are absorbed and redistributed. Different species respond in different ways, buffering the whole against collapse. In a simplified system, there are fewer backup options. A change in temperature, chemistry, or nutrient supply can push the system further into instability. Geologists see this simplification reflected in rock layers. Fossil assemblages shrink. Certain groups vanish abruptly, while others linger at low diversity. Sediments become enriched in organic matter because there are fewer oxygen-dependent organisms to break it down. The colour of the rock itself changes, recording the absence of oxygen at the time it formed. There is also a spatial component to this kind of death. It doesn't affect the entire ocean uniformly at first. Anoxic zones often begin in deeper waters or in restricted basins where circulation is weak. Over time, these zones can expand, merging with others and covering vast areas. The habitable portion of the ocean becomes fragmented, split into isolated pockets separated by inhospitable conditions. For organisms living through this, the world becomes smaller. Migration routes close, breeding grounds disappear. Even species that might tolerate low oxygen find themselves trapped by geography or temperature. Extinction doesn't always come from direct suffocation. It comes from isolation, from being unable to reach food or reproduce successfully. This is why the phrase "the ocean nearly died" is used. It reflects the loss of complexity and connectivity rather than the absence of life itself. The ocean remained, but its role as a cradle of diverse ecosystems was severely diminished. For long periods, it functioned more like a chemical reactor than a biological network. Understanding this distinction matters because it changes how we think about environmental collapse. It's not always about total destruction. Often, it's about thresholds. Cross them, and the system reorganizes into something less capable of supporting the richness that once existed. Recovery then requires not just time, but a reversal of the conditions that caused the collapse in the first place. In the case of ancient anoxic events, that meant changes in climate, tectonics, and circulation patterns. It meant cooler temperatures, stronger mixing, and reduced nutrient input. Only when oxygen could once again penetrate deep waters did complex ecosystems begin to re-establish themselves. Even then, the new ocean was not the same as the old one. Evolution had moved on. New groups filled niches left vacant. Some losses were permanent. The ocean didn't return to its previous state. It became something else. This idea of death as transformation rather than erasure is central to understanding Earth's history. It applies not only to oceans but to forests, reefs, and even the atmosphere itself. Systems don't vanish. They shift. They simplify or complicate depending on conditions, and those shifts can last far longer than the events that triggered them. As we move forward, the focus naturally turns toward the mechanisms that made oxygen such a fragile linchpin in all of this. Why something so common in the air above us can be so easily lost below the surface, and how an ancient agreement between life and chemistry, once disrupted, allowed the ocean to drift into a state where silence, in the ecological sense, became the dominant condition. Beneath the surface of the ocean, far below the reach of light and weather, there exists a balance that is easy to overlook precisely because it usually works so quietly. It isn't a balance enforced by a single force or controlled from one place. Instead, it emerges from countless small interactions layered over immense distances and long spans of time. Water temperature, salinity, pressure, chemistry, biology, and the slow turning of the planet itself all play a role. When this balance holds, the ocean appears stable, even eternal. When it begins to slip, the consequences unfold slowly enough to escape notice, until they can no longer be ignored. At its core, the ocean is not a static container of water. It is a moving system, constantly redistributing heat, gases, and nutrients. Surface waters exchange oxygen and carbon dioxide with the atmosphere. Wind pushes water into motion. Differences in temperature and salinity create density gradients that drive sinking and rising. Together, these processes form a vast circulation network that links the surface to the depths. This circulation is not fast. Some deep ocean waters take hundreds or even thousands of years to complete a full loop. But speed is not the point. Consistency is. Oxygen enters the ocean primarily at the surface, dissolving into seawater from the air. Cold water holds more oxygen than warm water, which is why polar regions are so important. When cold, salty water becomes dense enough, it sinks, carrying oxygen with it into the deep ocean. This sinking motion, is one of the few reliable ways oxygen reaches depths where sunlight never penetrates. Without it, the deep ocean would slowly lose oxygen as organisms consume what little remains. At the same time, nutrients move in the opposite direction. Organic matter produced near the surface sinks as particles, feeding life below. As it decomposes, nutrients are released back into the water, eventually returning to the surface through upwelling and mixing. This exchange supports productivity and keeps ecosystems supplied without allowing any one component to accumulate unchecked. This is the hidden balance. Oxygen down, nutrients up, heat redistributed, waste products diluted, life supported not by abundance in any single place, but by movement between places. When conditions are right, this balance is remarkably resilient. The ocean can absorb disturbances, adjust in circulation patterns and biological activity to compensate. But that resilience has limits. Push the system too far in one direction, and the feedbacks that normally stabilize it begin to amplify the problem instead. One of the most important factors in maintaining this balance is temperature. As surface waters warm, their density decreases. Warm water resists sinking, even if it is salty. This creates stronger stratification, a clearer separation between surface and deep layers. Stratification itself is not inherently bad. It exists in today's ocean as well. But when it intensifies beyond a certain point, vertical mixing weakens. Oxygen delivery to depth slows. At first, the deep ocean can cope. Oxygen levels decline gradually, and many organisms are adapted to low oxygen environments. But as stratification persists, oxygen consumption continues without adequate replacement. Decomposition of sinking organic matter steadily draws oxygen down. Over time, the balance tips. Another key factor is nutrient input. Nutrients are essential for life, but like oxygen, they must be regulated. When nutrient delivery increases significantly, productivity near the surface rises. More plankton grow, more organic matter sinks. This increased export of carbon to deeper waters accelerates oxygen consumption below. In a well-mixed ocean, this effect is moderated. In a stratified one, it becomes dangerous. What makes this especially tricky is that warming and nutrient input often increase together. Warmer climates tend to intensify weathering on land. Rainfall patterns shift, delivering more nutrients into rivers and coastal waters. Volcanic activity can also contribute, releasing gases and ash that fertilize the ocean. These inputs don't act in isolation. They interact with circulation changes, reinforcing the same trend. As oxygen declines, biological communities respond in ways that further alter the balance. Animals that normally stir sediments and circulate oxygenated water into the seafloor disappear. Without their activity, sediments become more stagnant. Chemical gradients sharpen. Processes that consume oxygen become more efficient, while those that replenish it weaken. In these conditions, microbes adapted to low or zero oxygen flourish. Their metabolisms often rely on compounds like sulfate instead of oxygen. While this allows them to thrive where others cannot, it also produces byproducts that further degrade conditions for oxygen-dependent life. Hydrogen sulfide in particular accumulates and spreads, making previously marginal habitats completely uninhabitable for complex organisms. The balance beneath the waves is not just physical and chemical, it is biological. Animals and microbes actively shape their environment. Remove one group and the others respond. Sometimes those responses stabilize the system. Other times they push it further toward collapse. One of the most deceptive aspects of this process is how invisible it is from above. The surface ocean can remain productive and visually unchanged even as conditions deteriorate below. Photosynthesis continues. Algae bloom. From a surface perspective, the system may even appear more alive than before. But this productivity is drawing down oxygen elsewhere, storing up problems that will emerge later. This disconnect between surface appearance and deep reality is why ancient anoxic events took so long to recognise in the geological record. Early researchers focused on surface fossils and obvious extinction markers. It was only when geochemical evidence accumulated, when black shales and trace metal patterns were analysed in detail, that the extent of deep ocean oxygen loss became clear. The hidden balance also explains why recovery from anoxic conditions is so slow. Restoring oxygen to deep waters requires more than simply reducing oxygen consumption. It requires re-establishing circulation. That means cooling surface waters, increasing density contrasts in the right places, and allowing sinking processes to resume. These are global changes, not local fixes. Even when oxygen begins to return, ecosystems don't snap back immediately. The deep ocean may remain oxygen poor for long periods, with habitable zones expanding only gradually. Species that vanish during the anoxic phase do not reappear unless there are surviving populations elsewhere. Evolution fills the gaps instead, often producing new communities rather than restoring old ones. This is why the concept of balance is so important here. It's not about maintaining a precise number or fixed state. It's about preserving movement, flow, exchange. The ocean's health depends on its ability to connect distant regions and different layers into a functioning whole. When that connectivity weakens, the system fragments. The deep ocean becomes isolated. The surface becomes overproductive. The middle layers, once rich with life, shrink or disappear. What remains is an ocean that still moves, still exists, but no longer supports the diversity and complexity that once defined it. As we continue, the next step is to look more closely at one of the key players in this balance: oxygen itself. How it enters the ocean, how it moves, and why its presence, despite seeming so fundamental, is surprisingly easy to disrupt. Because once oxygen's role is fully understood, the chain of events that led the ocean towards silence becomes even clearer, and the fragility of that hidden balance beneath the waves comes sharply into focus. Oxygen feels so fundamental to life now that it's easy to forget how unusual its role really is. We breathe it without effort. We associate it instinctively with vitality, energy, and movement. In the modern world, oxygen seems abundant, stable, and ever-present, especially when measured against the vastness of the atmosphere and the scale of the oceans. But this sense of permanence is misleading. Oxygen's relationship with life is not guaranteed. It is the result of an ancient agreement, one that took billions of years to form and that can unravel under the right conditions. Early life on Earth did not need oxygen at all. For a long time, oxygen was not just absent, it was actively hostile to many organisms. The first living systems evolved in an oxygen-free world, using chemical pathways that relied on sulfur, iron, and other elements to generate energy. These anaerobic metabolisms were sufficient for simple life, but they placed strict limits on size, speed, and complexity. Energy yields were low, growth was slow, ecosystems were thin and localized. The gradual rise of oxygen changed everything. It didn't happen overnight. Photosynthetic organisms began producing oxygen as a waste product long before the atmosphere became oxygen-rich. For millions of years, that oxygen was quickly consumed by reactions with rock, iron, and other reduced materials. Only once those sinks became saturated did oxygen begin to accumulate in the air and oceans. This shift opened the door to a more efficient way of extracting energy from food. Oxygen-based metabolism allows organisms to release far more energy from organic molecules than anaerobic processes. This surplus energy made larger bodies possible. It supported active movement, nervous systems, predation, and complex reproduction. Over time, life reorganized itself around oxygen availability. Ecosystems expanded vertically and horizontally. Food webs lengthened. The ocean became a layered, dynamic environment where oxygen shaped who could live where. But this new arrangement came with a vulnerability. Once organisms committed to oxygen, they became dependent on it. Their physiology, behavior, and life cycles evolved under the assumption that oxygen would be present, at least in small but reliable amounts. Remove it, and those adaptations turn into liabilities. In the ocean, oxygen availability is uneven by nature. Surface waters are usually well oxygenated due to contact with the atmosphere and photosynthesis. Deeper waters receive oxygen only through circulation. As organic matter sinks and decomposes, oxygen is consumed. This creates natural gradients. Many organisms have evolved to live near the edge of hypoxia, tolerating low oxygen where competition is reduced. But even these specialists rely on a minimum threshold. The agreement between oxygen and life is therefore conditional. Life can tolerate fluctuations, but only within limits. When oxygen falls below those limits across large areas, the system doesn't gradually adapt, it breaks down. During ancient anoxic events, this agreement failed on a massive scale. Oxygen delivery slowed while consumption increased. What made the situation particularly dangerous was that oxygen loss didn't occur in isolation. It was tied to other changes that reinforced its decline. Warmer temperatures reduced solubility, meaning water physically held less oxygen. Stratification prevented mixing. Nutrient-driven productivity accelerated decomposition. Each factor alone might have been manageable. Together they overwhelmed the system. As oxygen declined, life faced a narrowing set of choices. Organisms that could move attempted to escape, migrating towards shallower or more oxygenated waters. But these refugees were limited. Competition intensified. Predation pressures shifted. Species that relied on specific depth ranges or habitats found themselves trapped. Sessile organisms, those fixed in place, had no escape at all. Reef builders, filter feeders, and benthic animals were particularly vulnerable. Their disappearance removed important structural elements from ecosystems. Reefs that once provided shelter and feeding grounds collapsed. Sediments that had been stabilized by biological activity became prone to chemical stagnation. Microbial communities responded quickly. Bacteria capable of anaerobic metabolism expanded, filling ecological space left vacant by oxygen-dependent life. These organisms were not newcomers. They had always been present, quietly operating in low oxygen niches. When conditions shifted, they simply took advantage of an opportunity. This microbial takeover altered the chemistry of the ocean in ways that made recovery harder. Anaerobic processes often produce reduced compounds that consume oxygen when it becomes available again. Hydrogen sulfide, methane, and ammonium accumulated. These substances reacted with metals, altered nutrient cycles, and created chemical environments hostile to returning oxygen-dependent organisms. In effect, the ocean became self-reinforcing in its oxygen-poor state. The longer anoxia persisted, the more the system adapted to it, and the harder it became for oxygen to re-establish itself. From a biological perspective, this represents a collapse of trust. Life had invested in oxygen. It had built complexity around it. When oxygen failed, there was no quick fallback. Evolution works on long timescales. Populations cannot simply switch metabolisms or redesign their physiology in response to rapid environmental change. Extinction filled the gap where adaptation could not. Yet even in this collapse, life did not disappear. It reorganized. Simpler systems replaced complex ones. The ocean continued to function, but in a diminished capacity. Energy flowed through shorter, less intricate pathways. Diversity shrank. Stability came at the cost of richness. This is why oxygen's role must be understood not just as a chemical fact but as a relationship. It is a mediator between physical processes and biological possibility. Its presence or absence shapes the architecture of ecosystems. Its stability determines whether complexity can persist. The fragility of this agreement becomes clearer when we consider how thin the margins really are. In many parts of the modern ocean, oxygen levels are already low enough that small changes can have outsized effects. Regions known as oxygen minimum zones sit close to critical thresholds. Slight warming or increased nutrient input can push them into hypoxia. The difference between a functioning ecosystem and a collapsed one can be measured in tiny concentrations. Ancient anoxic events show us what happens when those thresholds are crossed on a global scale. They're reminders that oxygen is not guaranteed simply because it exists in the atmosphere. Delivering it to the deep ocean requires circulation, temperature gradients, and biological moderation to all work together. When one of these components falters, the agreement begins to unravel. When several fail at once, the unravelling accelerates. Understanding this ancient relationship also reframes how we think about resilience. The ocean did not recover because oxygen magically returned. It recovered because the physical conditions that support oxygen delivery were restored, cooling climates strengthened circulation, nutrient inputs stabilised, stratification weakened. Only then could oxygen once again penetrate deep waters consistently enough to support complex life. Even then, recovery was uneven. Some regions rebounded faster than others. Some lineages returned. Others were gone forever. The agreement was rewritten, not restored exactly as it had been. As this story continues, the focus naturally shifts toward how temperature, circulation and chemistry conspired to tip the balance in the first place. Because once oxygen's fragility is understood, the warming of the ocean takes on a new significance. It becomes clear that heat alone was not the enemy, but that heat altered the very terms of the agreement between life and oxygen, setting the stage for a slow, quiet collapse that unfolded beneath the waves. Warmth has a way of changing systems without announcing itself. It doesn't arrive with a single moment you can point to and say, "This is when everything shifted." Instead, it alters probabilities. It nudges processes that were once balanced into new configurations. In the ocean, warmth does not simply make water hotter. It changes how water behaves, how it moves, what it can carry, and how life within it is allowed to function. During the periods leading up to major anoxic events, rising temperatures quietly rewrote the rules that had governed the sea for millions of years. In a cooler world, the ocean is more willing to mix. Cold water is dense. When surface waters cool, especially at high latitudes, they sink readily, pulling oxygen from the atmosphere down into the depths. This sinking motion is one of the engines of global circulation. It creates deep currents that move slowly but persistently, ventilating the ocean interior and keeping oxygen levels above critical thresholds. Heat disrupts this process at its foundation. As global temperatures rose in the past, surface waters warmed across much of the planet. Warm water expands and becomes lighter. Even small increases in temperature can significantly reduce density, especially when spread over large areas. Once surface water becomes buoyant enough, it resists sinking, even when winds or seasonal cooling try to push it downward. The vertical connection between surface and deep layers weakens. This doesn't shut circulation down instantly. At first, it slows it. Sinking still occurs in limited regions or during colder seasons, but the volume of water involved decreases. Oxygen delivery to the deep ocean becomes less frequent and less uniform. Some basins continue to receive ventilation, others begin to stagnate. At the same time, warmth changes how much oxygen water can physically hold. Cold water can dissolve more oxygen than warm water. As temperatures increase, even oxygenated surface waters carry less oxygen into the ocean than before. This means that every unit of water sinking into the depths delivers a smaller oxygen payload. Consumption below remains the same or increases, but supply shrinks. Warmth also reshapes the boundaries between layers of the ocean. Thermoclines, the zones where temperature changes rapidly with depth, become sharper and more stable. These layers act like barriers, resisting vertical movement. Nutrients, oxygen, and organisms find it harder to cross them. The ocean becomes more compartmentalized, less fluid in its internal exchanges. This stratification has consequences for life at the surface as well. Warmer conditions often enhance biological productivity. especially when nutrients are abundant. Phytoplankton respond quickly to favourable temperatures and nutrient inputs, growing rapidly and forming large blooms. On the surface, this can look like vitality. The ocean appears busy, productive, alive, but this productivity carries a cost that is paid below. When plankton die, they sink. Their remains drift downward, feeding bacteria that consume oxygen as they break organic matter apart. In a strongly stratified ocean, this decomposition happens in waters that are no longer being refreshed with oxygen from above. Consumption accelerates depletion. Warmth, by stimulating productivity and restricting ventilation at the same time, tightens the trap. There is another way warmth alters the system, and it lies in how it affects land. Warmer climates intensify chemical weathering. Rainfall patterns change. More nutrients are flushed from soils into rivers and eventually into the sea. Phosphorus and nitrogen, essential for life, arrive in greater quantities. These nutrients fertilize the ocean, driving even more surface productivity. Once again, the effects reinforce one another. Warmth strengthens stratification. Stratification limits oxygen delivery. Nutrients boost productivity. Productivity increases oxygen consumption at depth. The system moves steadily toward imbalance without requiring a single catastrophic trigger. What makes this particularly dangerous is that the feedbacks involved are asymmetric. It is easier to lose oxygen than to regain it. Oxygen depletion can happen gradually but persistently. Recovery requires not just a halt in consumption, but a restoration of circulation strong enough to overwhelm the accumulated deficit. Warmth pushes the system in the wrong direction on both fronts. In ancient oceans, geography amplified these effects. Continents were arranged differently. Shallow seas covered large portions of the planet. Restricted basins formed where water exchange with the open ocean was limited. These environments were especially sensitive to warming. Once stratification set in, they became natural traps for anoxia. Even the deep open ocean was not immune. As circulation slowed globally, oxygen-poor waters expanded laterally and vertically. What began as isolated low-oxygen zones grew, merged and spread. Habitable space contracted not because the ocean was shrinking, but because its internal structure no longer supported life at depth. For organisms living through this transition, the rules they had evolved under were quietly changing. Oxygen was no longer a stable background condition. Temperature gradients shifted. Food availability fluctuated unpredictably. Migration patterns that once worked led into dead ends. Breeding grounds deteriorated. Warmth also influenced evolutionary pressures in subtler ways. Higher temperatures speed up metabolic processes. Organisms require more oxygen to maintain the same level of activity. In a warming, oxygen-poor ocean, this creates a physiological squeeze. Demand rises while supply falls. Species already living near their tolerance limits are pushed beyond them. This mismatch is particularly lethal for large-bodied and highly active organisms. They need more oxygen per unit time. Smaller, slower, or more metabolically flexible organisms fare better. Over time, this bias reshapes ecosystems. Size distributions shift. Predator-prey relationships change. Energy flows through different channels. The ocean does not announce these changes. There is no single signal that says the rules have been rewritten. Instead, the effects accumulate. Diversity declines. Fossil assemblages thin out. Chemical signatures shift. Only in hindsight does the pattern become clear. Warmth did not act alone. It did not cause anoxia by itself, but it set the stage. It weakened the mechanisms that maintained oxygenation, while strengthening those that consumed oxygen. It made the ocean more productive and less ventilated at the same time. It turned stability into fragility. Once this new set of rules took hold, reversing them required more than a pause in warming. The system needed cooling strong enough to re-establish density-driven circulation. It needed time for accumulated organic matter to be processed or buried. It needed a reduction in nutrient input. These conditions did not arrive quickly. This is why anoxic events persisted for such long periods. The ocean had settled into a warm, stratified state that was internally consistent, even if it was hostile to complexity. Life adapted to the new rules as best it could. Microbial systems flourished. Simpler food webs stabilized. The ocean did not recover until the rules changed again. Understanding how warmth altered the sea helps explain why oxygen loss was not a temporary glitch, but a sustained transformation. It shows how climate and ocean chemistry are inseparable, and it leads naturally to the next piece of the story, because once warmth strengthened stratification, the movement of water itself began to slow in ways that further isolated the deep ocean, allowing stagnant conditions to spread and settle in for the long haul. Stagnation does not arrive with force, it arrives quietly, carried by small changes that seem harmless on their own. In the ocean, stagnant water is not water that stops moving entirely. Currents still exist, tides still pull, but the deep, persistent exchanges that once refreshed entire basins weaken, until large volumes of water become isolated from the rest of the system. When this happens slowly enough, the ocean does not resist. It adapts, and in adapting it drifts into a state that is difficult to escape. In a well-ventilated ocean, no parcel of water remains cut off for very long. Even the deepest layers are eventually reached by oxygenated water sinking from the surface. This renewal happens on long time scales, but it happens reliably. The deep ocean is slow, not stagnant. During the lead up to major anoxic events, that distinction began to blur. As surface warming intensified stratification, the formation of deep water weakened. Fewer regions produced dense enough water to sink. Those that still did produced smaller volumes. The deep currents fed by this sinking slowed, becoming thinner and more fragmented. Entire pathways of circulation weakened or shut down. Water that once moved, however, gradually now lingered. This lingering had consequences. Every breath the ocean took through circulation was delayed. Oxygen already present in deep waters continued to be consumed by respiration and decomposition. But without regular replacement, levels declined steadily. At first, this decline was uneven. Some areas remained better ventilated than others. Patchiness increased. Oxygen-poor zones formed in pockets. Over time, those pockets expanded. Stagnant waters behave differently than well-mixed ones. Chemical gradients sharpen. Compounds that would normally be diluted or transported away begin to accumulate. Reduced substances like iron and sulfide build up in sediments and then leak back into the water column. Nutrients recycle locally rather than being spread across basins. The system becomes internally focused, recycling its own products instead of exchanging them widely. Biological activity responds to this isolation. In stagnant zones, organisms that depend on steady oxygen delivery disappear. Those that can tolerate poor conditions persist, but often in lower diversity. The loss of burrowing animals changes sediment structure, making it denser and less permeable. This further restricts oxygen penetration, even when small amounts are available. What begins as sluggish circulation becomes a reinforcing cycle. Slower movement leads to oxygen loss. Oxygen loss alters chemistry and biology. Those changes make it harder for circulation to resume its previous role. The system locks itself into a stagnant mode. This process is not uniform across the ocean. Geography matters. Deep basins with limited connections to other regions are especially vulnerable. Once circulation weakens, these basins effectively trap water masses for long periods. Oxygen levels can fall to zero and remain there, even if neighbouring regions are better ventilated. Shallow epicontinental seas also play a role. These broad, shallow areas, common during warm periods with high sea levels, are prone to poor circulation. Water exchange with the open ocean is limited. Stratification can develop easily. organic matter production is often high due to nutrient input from land. Together, these factors make shallow seas hotspots for stagnation. As stagnant conditions spread, the deep ocean becomes increasingly uniform in its oxygen deprivation. Variability decreases. Instead of a mosaic of environments, large regions share the same low oxygen state. This uniformity favours microbial communities adapted to these conditions. Diversity drops, but stability increases. From the perspective of chemical cycles, stagnation alters how elements move through the ocean. Carbon burial increases as organic matter escapes decomposition. Phosphorus can become trapped in sediments or recycled in ways that enhance productivity further. Nitrogen cycling shifts toward pathways that release nitrogen gas, potentially limiting some forms of life while favouring others. These changes do not stay confined to the deep. Over long periods, stagnant waters can influence surface conditions as well. Upwelling brings nutrient-rich but oxygen-poor water toward the surface. This fuels productivity while maintaining hypoxia below. The contrast between a productive surface and a suffocating interior becomes sharper. For organisms living in mid-water depths, this is particularly disruptive. These zones, often rich in biodiversity under normal conditions, shrink dramatically. Species that rely on vertical migration find their pathways blocked by inhospitable layers. Energy transfer between surface and deep ecosystems weakens. Stagnation also affects temperature distribution. Without mixing, heat remains trapped near the surface. The deep ocean cools slowly, if at all. This thermal isolation reinforces stratification, making it even harder for sinking to resume. Once again, the feedback favours persistence of the stagnant state. One of the most striking aspects of this process is its timescale. Stagnation does not need to be extreme to be effective. Even modest reductions in circulation, sustained over tens of thousands of years, can transform the ocean interior. By the time conditions are clearly anoxic, the groundwork has been laid for a very long time. In the geological record, this creep of stagnation is difficult to see directly. Water movement does not fossilise. Instead, scientists infer it from indirect clues. Trace metal distributions change, isotopic signatures shift, sediment composition evolves. Each piece alone is ambiguous. Together they tell a story of water that stopped being refreshed. The absence of oxygen-loving organisms in deep water sediments reinforces this picture. Where diverse communities once lived, only microbial traces remain. Burrows disappear. Layers become finely laminated, indicating little disturbance. These sediments speak of stillness, not in the sense of absolute calm, but in the sense of isolation. Once stagnation becomes widespread, reversing it requires significant change. Cooling must be strong enough to overcome stratification. New pathways of circulation must open. In some cases, tectonic shifts altering basin geometry may be necessary. Until then, stagnant waters persist, shaping life above them and chemistry below. This persistence is what makes the slow creep so important. It explains why anoxic events were not brief interruptions. They were sustained states, maintained by the ocean's own internal feedbacks. The system was no longer merely reacting to external forcing. It had reorganized itself. Understanding this helps clarify why life struggled to regain complexity during these periods. Even if oxygen began to appear sporadically, the stagnant framework prevented it from spreading effectively. Habitable zones remained fragmented. Recovery was delayed. As this stagnation deepened, another transformation became increasingly visible in the geological record. Dark, organic-rich sediments accumulated on the seafloor, preserving evidence of the ocean's breathless state. These layers would later become some of the clearest markers of anoxia, recording not just the absence of oxygen, but the long-term stagnation that allowed the ocean's darkest memories to settle and harden into stone. When scientists first began to piece together the story of ancient anoxic events, They did not start with oxygen sensors or direct measurements. Those tools did not exist for oceans hundreds of millions of years old. Instead, they began with rock. Dark, fine-grained layers preserved in cliffs, road cuts, drill cores and mountainsides. These rocks did not stand out because they were rare. They stood out because they were persistent, widespread and strangely uniform across vast regions of the planet. They were black shales, and they carried the ocean's memory of a time when breathing became difficult. Black shales form under specific conditions. They are rich in organic carbon, meaning large amounts of once-living material were buried and preserved rather than broken down. In a normal oxygenated ocean, this does not happen easily. Organic matter sinking to the seafloor is typically consumed by bacteria and animals. Oxygen allows microbes to efficiently decompose this material, recycling nutrients back into the water. Only a small fraction escapes burial. When oxygen is scarce or absent, that process changes. Decomposition slows dramatically. Bacteria that rely on oxygen are replaced by slower anaerobic processes. As a result, more organic material accumulates and becomes trapped in sediment. Over time, layer upon layer builds up, creating dark, carbon-rich rock. The black colour comes from finely dispersed organic compounds and minerals formed under reducing conditions. What makes black shales especially important is not just how they form, but where they form. During anoxic events, these sediments appear across entire ocean basins. They're found in what were once deep waters, shallow seas, continental margins, and restricted basins. Their global distribution tells us that oxygen depletion was not a local accident. It was a systemic feature of the ocean. These rocks act like a long-term archive. They record chemical conditions that existed at the seafloor when they formed. Trace metals such as molybdenum, uranium and vanadium behave differently in oxygen, rich versus oxygen-poor environments. In anoxic waters, these elements become more soluble and are readily incorporated into sediments. Elevated concentrations of these metals in black shales serve as fingerprints of oxygen depletion. Sulfur isotopes add another layer of information. The presence of pyrite, an iron sulfide mineral, indicates active sulfate reduction by bacteria, a process that occurs only when oxygen is absent. The size, shape, and abundance of pyrite grains reveal how widespread and persistent anoxia was. In many black shales associated with major anoxic events, pyrite is abundant and finely distributed, suggesting long-term, stable anoxic conditions rather than brief interruptions. The lamination of black shales also tells a story. In oxygenated environments, sediments are disturbed by burrowing organisms. Worms, crustaceans and other benthic animals mix layers together, erasing fine-scale structures. In anoxic conditions, these organisms are absent. Sediments settle undisturbed, forming thin, delicate layers that remain intact. These laminations are a direct signal of biological absence, a quiet testimony to a seafloor where few complex animals could survive. Black shales also preserve information about surface conditions. Organic matter buried within them often originates from plankton living in sunlit waters above. By analysing the composition of this organic material, scientists can infer what kinds of organisms dominated the surface ocean during these events. In many cases, there is evidence of high productivity, with large amounts of algae and cyanobacteria contributing to the carbon pool. This combination of high surface productivity and deep anoxia is a hallmark of anoxic events. It reflects the imbalance created when nutrient-rich waters fuel growth at the surface, while restricted circulation prevents oxygen from reaching depth. Black shales are the physical manifestation of that imbalance, locking away both the excess carbon and the evidence of oxygen loss. Over geological time, these shales do not remain isolated records. They become part of larger cycles. The burial of organic carbon during anoxic events can influence atmospheric composition. By removing carbon dioxide from the system and storing it in sediments, black shale formation can contribute to long-term cooling. This negative feedback may help explain why some anoxic events eventually ended. The ocean's suffocation set in motion processes that slowly restored balance. But this restoration was neither quick nor gentle. Black shale deposition often continued for hundreds of thousands of years. In some cases, it occurred in pulses, reflecting fluctuations in climate, circulation, or nutrient input. These pulses are visible as repeating dark layers interspersed with lighter sediments, each one a reminder that the system hovered near a critical threshold. It is also important to recognize what black shales do not show. They rarely contain abundant fossils of complex animals. Their silence is not just chemical, but biological. Where diverse communities once lived, the record goes quiet. This absence reinforces the idea that these were not merely low oxygen intervals, but times when entire ecosystems collapsed. As researchers compared black shales from different periods, patterns emerged. Some anoxic events were more severe than others. Some were regional while others were nearly global. Certain intervals, such as those during the mid-Cretaceous, stand out for their extent and intensity. During these times, black shales appear on nearly every continent, indicating that much of the world's ocean was affected simultaneously. The ocean's dark memory is not limited to the past. Black shales continue to influence the present. Over millions of years, they can be buried, heated, and transformed into hydrocarbons. Many of today's oil and gas reserves originate from ancient black shales formed during anoxic events. In this way, the ocean's breathless intervals have shaped human history indirectly, fueling industries and economies long after the conditions that created them vanished. This connection underscores the longevity of the ocean's memory. Conditions that lasted for a few million years left marks that persist for hundreds of millions more. The rocks remember what the water no longer shows. Black shales also remind us that absence can be as informative as presence. They are records of what was missing as much as what was there. Missing oxygen, missing animals, missing mixing. Each dark layer is a snapshot of a system operating under constraints very different from today's norms. Interpreting these records requires care. Black shales can form under a range of conditions, and not every dark sediment indicates a global anoxic event. Local basins, restricted circulation, and unique geological settings can also produce similar rocks. This is why context matters. When black shales appear simultaneously across multiple regions, accompanied by consistent chemical signals and biological patterns, the case for widespread anoxia strengthens. As analytical techniques improved, scientists began to read these rocks with increasing precision. Isotope ratios revealed changes in global carbon cycling. Trace metal profiles map the extent of oxygen depletion. Microfossils provide clues about surface ecosystems. Together, these lines of evidence transform black shales from simple dark layers into detailed narratives. What emerges from this narrative is not a picture of sudden catastrophe, but of prolonged stress. The ocean did not flip a switch. It drifted into a state where oxygen was no longer reliably delivered to depth. Black shales accumulated quietly, layer by layer, as the system adjusted to its new reality. This quiet accumulation is part of what makes anoxic events difficult to imagine. We are accustomed to thinking in terms of dramatic change. But the ocean's most profound transformations often unfold slowly, almost invisibly, until their consequences become unavoidable. As the story moves forward, attention naturally shifts from the sediments themselves to the living world they represent by their absence. The black shales tell us that something was missing, but to understand the full impact, we need to look at what vanished from the ocean during these periods. The creatures that failed to survive, the ecosystems that collapsed, and the long shadows those losses cast over the history of marine life. The most striking thing about the fossil record during major anoxic events is not always what appears, but what doesn't. Entire groups of organisms that had been present for millions of years simply fade out. They do not go out in dramatic layers packed with shells or bones. They thin, fragment, and then stop appearing altogether. In many cases, there is no single boundary you can point to and say, this is where they died. Instead, there is a gradual quieting, a biological dimming that mirrors the chemical one taking place in the water around them. Marine ecosystems before these events were often complex and highly structured. Food webs extended across multiple levels, from microscopic plankton to large predators. Reef systems built by corals, sponges, and other calcifying organisms created physical habitats that supported countless species. Seafloors were busy places, churned by burrowing animals that oxygenated sediments and recycled nutrients. This complexity depended on oxygen not just being present, but being reliably available across depth and time. As oxygen levels declined, the first losses were often subtle. Species with narrow tolerances disappeared from certain regions but persisted elsewhere. Fossil assemblages became patchy. Some habitats retained diversity longer than others, creating the illusion that the system as a whole was still intact. But these were warning signs. The foundation was weakening. One of the hardest hit groups during anoxic events were benthic animals, those that lived on or within the seafloor. These organisms were directly exposed to declining oxygen in bottom waters. Burrowing species such as worms, small crustaceans and mollusks are particularly sensitive because their lifestyle depends on oxygenated sediments. As oxygen dropped, these animals either migrated, if possible, or died. Their disappearance had consequences far beyond their own survival. Without burrowers, sediments became compacted and stratified. Oxygen penetration into the seafloor decreased even further. Microbial processes shifted toward anaerobic pathways. Toxic compounds accumulated. This made the environment even less hospitable for animals that might otherwise have survived. The loss of benthic life was both a result of anoxia and a driver of its persistence. Reef builders also suffered greatly. Corals, calcareous sponges, and other organisms that create reef structures require stable, oxygen-rich conditions. They are sensitive not only to oxygen levels but also to changes in water chemistry associated with anoxia, such as increased acidity and the presence of sulfide. During major anoxic intervals, reef systems collapsed or failed to develop at all. In some periods, reefs are almost entirely absent from the geological record for millions of years. The loss of reefs had cascading effects. Reefs are biodiversity hotspots. They provide shelter, breeding grounds, and feeding areas for a wide range of species. When reefs vanished, the species that depended on them vanished too. This included many fish, invertebrates, and microorganisms that left little or no trace behind. Pelagic organisms, those living in the open water, were not immune. Many planktonic animals have specific oxygen requirements, especially during certain life stages. As oxygen-poor zones expanded upward, these organisms lost viable habitat. Vertical migration, a common strategy for avoiding predators or finding food, became dangerous or impossible. Layers that were once safe passageways turned into lethal barriers. Some groups of plankton disappeared entirely from certain regions. Others survived only in reduced diversity. Because plankton form the base of marine food webs, these losses reverberated upward. Fish populations declined. Large predators struggled to find enough prey. Ecosystems simplified. Perhaps the most haunting aspect of these extinctions is how incomplete the record can be. Many soft-bodied organisms do not fossilize well under normal conditions. In anoxic environments, preservation of organic material can be enhanced, but the absence of oxygen-dependent animals means there is simply less to preserve. Entire lineages may have vanished without leaving clear physical evidence of their existence, let alone their demise. This absence forces scientists to read between the lines. They infer losses from gaps in ecological structure, from sudden changes in sediment mixing, from shifts in chemical cycles that imply the removal of certain biological processes. It is a kind of negative evidence, one that requires careful interpretation. The pattern of loss also reveals something about survival. Organisms that persisted through anoxic events tended to share certain traits: small body size, low metabolic demand, flexible feeding strategies, tolerance for low oxygen or variable conditions. These traits allowed them to endure in refuges where conditions were marginal but not lethal. In contrast, large, active, specialized organisms were at a disadvantage. Their energy requirements were high, their ecological roles were narrow. When oxygen declined and food webs collapsed, they had few options. Extinction was not instantaneous, but it was often inevitable. It is important to note that these losses did not always coincide with dramatic extinction boundaries like those associated with asteroid impacts. Instead, they unfolded over extended intervals. Species declined gradually, sometimes disappearing region by region rather than globally at once. This makes anoxic events harder to recognize as mass extinctions in the traditional sense, even though their cumulative impact was enormous. Over time, the ocean became dominated by fewer kinds of organisms performing fewer kinds of roles. This simplification reduced the system's ability to respond to change. When conditions fluctuated, there were fewer buffers, fewer redundancies. Stability was maintained through uniformity rather than diversity. Eventually, as conditions began to improve, life did not simply return to its previous state. The organisms that had vanished did not reappear. Evolution filled the gaps with new forms, often with different strategies and structures. The post-anoxic ocean was not a restored version of what came before. It was a reassembled system built from survivors and newcomers. The creatures that vanished without a trace are therefore not just a list of losses. They represent entire ways of living that the ocean could no longer support under the new conditions. Their disappearance reshaped the trajectory of marine evolution, influencing which groups would dominate in the future. As we continue, attention naturally turns to the other side of this story. While many organisms disappeared, some managed to persist, adapting to conditions that would have been lethal to most life. These survivors hold important clues about resilience, tolerance, and the limits of biological flexibility in a world where oxygen was no longer a reliable constant. Not everything vanished when oxygen retreated from the ocean. While many familiar forms of life faded away, others endured, quietly occupying the shrinking spaces where survival was still possible. These survivors did not thrive in the way we usually imagine success. They persisted, they tolerated, they endured conditions that stripped away complexity and rewarded restraint. In doing so, they reshaped what the ocean was allowed to be for a very long time. Survival in a suffocating world required a particular set of traits. High-energy lifestyles reliability. Speed, large body size, and constant activity demanded oxygen that was no longer available. The organisms that made it through anoxic intervals tended to live slowly. They grew gradually, reproduced efficiently, and required minimal resources to maintain basic functions. In an ocean where oxygen was unreliable, efficiency mattered more than strength. Microorganisms were the clearest beneficiaries of these conditions. Bacteria and archaea capable of anaerobic metabolism expanded dramatically. These organisms had existed long before oxygen ever became common, and they never lost the ability to function without it. In oxygen-poor waters, they were no longer confined to marginal niches. They became the dominant processors of energy and matter. Different groups of microbes exploited different chemical pathways. Some used sulfate instead of oxygen to break down organic material, producing hydrogen sulfide as a byproduct. Others relied on nitrate, iron, or carbon dioxide. These processes kept the ocean chemically active even when oxygen-dependent life collapsed. From a purely biochemical perspective, the system was still running. It was just running on older, less efficient rules. Among multicellular life, survival was more selective. Small-bodied animals with low metabolic demands fared better than large ones. Some worms, for example, can tolerate extremely low oxygen levels by slowing their metabolism and relying on anaerobic pathways for short periods. Certain mollusks can close their shells and wait out unfavourable conditions, reducing oxygen consumption to a minimum. Zooplankton communities also shifted. Species with flexible life cycles, capable of adjusting growth rates or reproduction timing, had an advantage. Those that could exploit brief windows of oxygen availability or live near the surface where oxygen was more abundant were more likely to persist. Even so, diversity within these groups declined. Fish and other active swimmers were among the most challenged. Some species retreated to surface waters or migrated laterally to regions where circulation remained stronger. These refuges were limited and often crowded. Competition increased. Predation patterns shifted. Many lineages disappeared entirely, while others survived only in restricted regions. One important factor in survival was tolerance for chemical stress beyond oxygen deprivation. Anoxic waters often contained elevated levels of hydrogen sulfide, which is toxic to most animals. Very few multicellular organisms can tolerate sulfide for long. Those that could often possessed specialized biochemical adaptations, such as sulfide-binding proteins or symbiotic relationships with bacteria that detoxified their environment. These symbioses became particularly important. Some surviving animals formed close partnerships with anaerobic or sulfide-oxidizing bacteria. The bacteria processed toxic compounds or provided alternative energy sources, while the host offered protection and access to nutrients. These relationships allowed certain organisms to occupy environments that would otherwise have been uninhabitable. The existence of these survivors challenges the idea that anoxic events were periods of complete devastation. Life did not disappear. It reorganized around a narrower set of viable strategies. The ocean became less about interaction between many different kinds of organisms and more about persistence under constraint. This reorganization had long-term consequences. Ecosystems dominated by tolerant species are stable in a limited sense. They can persist under harsh conditions without dramatic change. But they are also less dynamic. Innovation slows. The range of ecological roles narrows. Evolution continues but along restricted pathways. Over hundreds of thousands or millions of years, these survivor communities became the default state of the ocean. New species evolved within these constraints, often inheriting tolerance rather than complexity. The longer anoxic conditions lasted, the more entrenched these systems became. Importantly, survival did not mean immunity. Even tolerant organisms live close to their limits. Fluctuations in temperature, chemistry, or nutrient supply could still cause local collapses. Refuges shifted. Populations waxed and waned. Stability was relative, not absolute. As oxygen occasionally returned to certain regions, even temporarily, these survivors were often the first to respond. They expanded into newly habitable areas, sometimes outcompeting organisms that might otherwise have recolonized. This gave them a head start in shaping post-anoxic ecosystems. However, when full recovery eventually occurred and oxygen became reliably available again, the ocean did not simply revert to its previous inhabitants. Many of the pre-anoxic lineages were gone forever. The survivors and their descendants formed the foundation of new ecosystems. The future ocean was built not by restoring what was lost, but by amplifying what endured. This pattern highlights an important truth about survival during global crises. Persistence is not the same as preservation. What survives shapes what comes next, often in ways that permanently alter the character of the system. The ocean after an anoxic event was not healed in the sense of returning to a former state. It was transformed. Looking back through this lens, anoxic events can be seen not only as times of loss, but as filters. They removed organisms dependent on stable, oxygen-rich conditions and favoured those capable of tolerating variability and scarcity. This filtering influenced the direction of marine evolution long after oxygen levels recovered. As we move forward, this raises an important question. What forces were powerful enough to push the ocean into such a suffocating state in the first place? Survival explains persistence, but it does not explain cause. To understand why these conditions arose repeatedly in Earth's history, we need to look beyond the ocean itself, toward the planet's interior and the processes that reshaped the atmosphere and climate from below. The ocean did not suffocate on its own. It responded to pressures that originated far beyond the waves, forces that worked on planetary scales and over immense spans of time. To understand why oxygen retreated so persistently during these ancient intervals, it is necessary to look upward and downward at once. Upward to the atmosphere that regulates heat and gas exchange. Downward to the restless interior of the Earth, where heat and chemistry continually reshape the surface world. Between these realms lies a story of carbon, volcanism, and a sky that refused to remain stable. Volcanoes are often imagined as brief, violent interruptions, explosions, ash clouds, lava flows that cool and harden within years or decades. But the kind of volcanism most closely associated with major anoxic events was different. It was vast, sustained, and quiet enough that it did not always leave obvious scars in a single location. Instead of isolated eruptions, entire regions of the planet released enormous amounts of volcanic material over hundreds of thousands, sometimes millions of years. These episodes are known today as large igneous provinces. They occur when massive volumes of magma rise from deep within the mantle and spread across the surface through extensive fissures. Lava pours out repeatedly, covering huge areas. The scale is difficult to grasp. Individual events can produce enough volcanic rock to blanket continents, but equally important as the lava itself are the gases released alongside it. Volcanic activity is a major source of carbon dioxide. When magma rises, dissolved gases escape into the atmosphere. Carbon dioxide accumulates, along with methane and other greenhouse gases. Unlike short-lived volcanic aerosols that can cool the planet temporarily, carbon dioxide persists. It builds up slowly but steadily, altering the planet's energy balance. As atmospheric carbon dioxide levels rose during these prolonged volcanic episodes, global temperatures followed. The greenhouse effect intensified. More heat was trapped near the surface. Oceans warmed. Ice diminished or vanished entirely. Sea levels rose. The climate shifted into a warmer state that favoured the very ocean conditions that lead to oxygen loss. This warming did not need to be extreme to be effective. Even moderate increases in temperature, sustained over long periods, were enough to alter circulation patterns and strengthen stratification in the ocean. Once again, the change was gradual. There was no single moment when the ocean suddenly became anoxic. Instead, the system drifted toward vulnerability as greenhouse gases accumulated. Carbon did more than warm the planet. It also altered chemical cycles. Higher carbon dioxide concentrations in the atmosphere increased the amount of carbon dioxide dissolving into the ocean. This changed seawater chemistry, affecting the balance between different forms of carbon and altering acidity. These changes influenced the organisms responsible for building shells and skeletons, many of which struggled under shifting conditions even before oxygen levels fell critically low. Meanwhile, volcanic activity affected land as well as sea. Fresh volcanic rock weathers quickly. Rainwater reacts with exposed basalt and other volcanic materials, drawing carbon dioxide out of the atmosphere through chemical reactions. At first glance, this might seem like a stabilizing influence. But weathering also releases nutrients, particularly phosphorus, into rivers and oceans. These nutrients fertilize marine ecosystems, boosting productivity at the surface. This creates a complex feedback. Volcanic carbon dioxide warms the climate, promoting conditions that lead to ocean stratification. Volcanic rock weathering delivers nutrients, increasing biological productivity. That productivity, in turn, increases oxygen consumption at depth. The same processes that eventually draw carbon dioxide back down through burial of organic matter also help drive the ocean toward anoxia in the short to medium term. The sky during these periods was not static. Carbon dioxide levels fluctuated as volcanic output waxed and waned, as weathering responded, and as organic carbon burial changed. Methane may also have played a role, especially during intervals when anoxic conditions expanded. Methane is produced by anaerobic microbes and can escape into the atmosphere from oxygen-poor waters. It is a powerful greenhouse gas, further amplifying warming. This atmospheric instability meant that the ocean was constantly adjusting to shifting boundary conditions. There was no prolonged return to cooler, well-mixed states until volcanic activity slowed significantly or tectonic configurations changed. As long as the sky remained loaded with greenhouse gases, the ocean remained predisposed to stagnation. One of the most challenging aspects of this process is that it operated on timescales far longer than those of individual organisms or ecosystems. Life could not wait it out. A species facing oxygen loss cannot simply persist for hundreds of thousands of years until conditions improve. Extinction occurred not because the environment was momentarily hostile, but because it remained hostile for longer than adaptation could accommodate. The connection between volcanism and anoxia is supported by timing. Many of the most severe anoxic events coincide closely with the emplacement of large igneous provinces. This pattern appears repeatedly in Earth's history. While not every volcanic episode caused widespread anoxia, and not every anoxic interval can be tied to a single volcanic source, the correlation is strong enough to suggest a shared mechanism. It is also important to note that volcanism did not act alone. Plate tectonics influenced ocean gateways, basin geometry, and continental positions. These factors shaped circulation patterns, determining how easily water could mix and how nutrients were distributed. In some configurations, the ocean was already prone to stagnation. Volcanic greenhouse forcing pushed it over the edge. The sky's refusal to rest, its persistent loading with carbon, meant that the ocean rarely had the opportunity to fully recover before being stressed again. Even as carbon burial during anoxic events began to draw down atmospheric carbon dioxide, renewed volcanic input could counteract this effect. The system oscillated, but within a warm, high-carbon envelope that favoured oxygen loss. This interplay between Earth's interior and its surface highlights an important point. Anoxic events were not accidents. They were emergent properties of how the planet operates when certain thresholds are crossed. Heat from below, carbon in the air, nutrients from the land, and circulation in the sea combined to produce a state that, once established, could persist for extraordinarily long periods. The ocean was not merely a passive victim in this process. It participated actively, storing carbon, redistributing heat, and shaping atmospheric composition through gas exchange. But its responses were constrained by physics and chemistry. Warm water stratifies, oxygen becomes scarce, microbial processes take over. The rules follow inevitably from the conditions. As the planet continued to change, eventually the balance began to shift again. Volcanic output declined. Weathering intensified. Carbon burial accumulated. The sky slowly shed some of its greenhouse load. Cooling crept back into the system, but the ocean did not immediately respond. Its inertia, the memory stored in its deep waters and sediments, meant that breath did not return quickly. This leads naturally to the next stage of the story. Once anoxic conditions were established, how long did they actually last? What did it mean for the ocean to remain breathless, not for a generation, but for spans of time that dwarf human history? To answer that, we have to look at duration, persistence, and the slow pace at which planetary systems heal after being pushed out of balance. When we try to imagine an ocean without oxygen, the instinct is to picture a temporary crisis, a bad interval, something that rises, peaks, and then fades within a time frame that still feels graspable. Years, maybe centuries, even thousands of years are difficult but not impossible to hold in mind. What makes ancient anoxic events so difficult to fully absorb is not only how severe they were, but how long they lasted. The ocean did not lose its breath briefly. In some cases, it remained breathless for spans of time that exceed the entire history of human civilization many times over. Geological time does not move the way personal time does. It does not hurry. It does not emphasize beginnings and endings. Instead, it stretches conditions out until they become states rather than events. When scientists estimate the duration of major anoxic intervals, they are not measuring isolated moments of oxygen loss. They're identifying long plateaus where oxygen remained consistently low across large portions of the ocean, with only minor fluctuations around a deeply altered baseline. Some anoxic events persisted for hundreds of thousands of years, others extended beyond 1,000,000 years. During these intervals, the ocean did not oscillate rapidly between healthy and unhealthy conditions. It stayed locked in a mode where oxygen delivery was insufficient. Circulation remained sluggish, and chemical feedbacks reinforced the absence of breathable water at depth. This persistence is one of the defining features of these events. It explains why their biological impact was so profound. A short-lived oxygen drop might kill some organisms, but it leaves survivors time to recolonize once conditions improve. A prolonged oxygen deficit removes that option entirely. Populations decline faster than they can recover. Extinction becomes not a dramatic endpoint, but a slow attrition. The duration of breathlessness varied from basin to basin. Some regions recovered sooner than others. Shallow areas with better circulation might have regained oxygen earlier, while deep basins remained anoxic for much longer. This created a patchwork of conditions across the global ocean. But even this patchwork operated within a broader framework of reduced oxygen availability. One reason these conditions lasted so long is that the processes that caused them were themselves long-lived. Volcanic carbon emissions did not spike and vanish. They accumulated over extended periods. Climate did not flip back to cooler states quickly. Stratification remained strong. Circulation pathways did not re-establish themselves easily once disrupted. Another reason lies in the ocean's internal inertia. Once deep waters become anoxic, simply restoring oxygen at the surface is not enough. Oxygen has to be transported downward, mixed, and distributed through layers that may not have been ventilated for tens or hundreds of thousands of years. That takes time even under favourable conditions. Sediments also play a role in prolonging breathlessness. During anoxic intervals, large amounts of organic matter accumulate on the sea floor. This buried carbon represents both a record of past productivity and a future oxygen sink. If oxygen begins to return, microbes and chemical reactions immediately start consuming it as they process this stored material. The seafloor effectively resists reoxygenation. This creates a lag between atmospheric or surface improvements and deep ocean recovery. Even if the sky begins to cool and circulation strengthens slightly, the deep ocean remains oxygen poor until enough oxygen has been delivered to overcome both ongoing consumption and the backlog created during the anoxic phase. Chemical feedbacks further slow recovery. Reduced compounds such as iron and sulfide accumulate during anoxia. When oxygen encounters these substances, it reacts rapidly, becoming bound or consumed. This means that early stages of reoxygenation may leave little trace in oxygen measurements. Oxygen arrives, reacts, and disappears before it can spread. From the perspective of life, this extended duration is critical. Evolution operates on long timescales, but it still requires viable populations to work with. When harsh conditions persist for hundreds of thousands of years, they do not just select for tolerant traits. They eliminate entire branches of the evolutionary tree. Recovery after such losses is not restoration, it is reinvention. The fossil record reflects this drawn-out timeline. Instead of sharp extinction boundaries, many anoxic events show prolonged intervals of reduced diversity. Species appear, disappear, reappear briefly, and then vanish again. This instability suggests that conditions hovered near critical thresholds for long periods, occasionally allowing limited recolonization before collapsing again. These false starts are important. They indicate that recovery was attempted many times but repeatedly failed. Oxygen may have increased slightly. Circulation may have strengthened temporarily. But the system as a whole was not ready to sustain a full return to oxygen-rich conditions. Each attempt stalled, and the ocean slipped back into breathlessness. This pattern also explains why some anoxic events are difficult to define precisely. There is no single start date, no clear end. Instead, there is a gradual onset, a prolonged core interval, and a drawn-out recovery. The boundaries blur. From a human perspective, this ambiguity is frustrating. From a geological perspective, it is expected. Another aspect of duration is how these events overlap with other changes. An anoxic interval might coincide with shifts in sea level, changes in biodiversity, or alterations in sedimentation patterns. These overlapping processes can mask or amplify the effects of oxygen loss. Untangling cause and effect requires careful comparison across multiple lines of evidence. Despite these complexities, one conclusion remains consistent. Once the ocean entered a breathless state, it tended to stay there until something fundamental changed in the planet's energy balance or circulation geometry. Minor adjustments were not enough. The system required a reset at a deep level. That reset often came slowly. Carbon dioxide levels had to decline significantly. This happened through enhanced weathering on land and increased burial of organic carbon in the ocean. Both processes operate on long timescales. As carbon dioxide gradually decreased, global temperatures cooled. Cooling strengthened density contrast in the ocean, allowing surface waters to sink more readily. As sinking resumed, oxygen delivery to depth improved incrementally, not dramatically, incrementally. Over many thousands of years, oxygenated water began to penetrate deeper layers. At first, only thin zones were affected. Habitable space expanded cautiously. Life responded tentatively. Opportunistic species moved in. Microbial communities shifted. Chemical conditions changed. But full recovery required persistence. Any reversal in climate or circulation could stall the process or reverse it altogether. This is why some anoxic events ended as gradually as they began. There was no moment when the ocean suddenly breathed again. Instead, oxygen crept back layer by layer, basin by basin. In some regions, anoxia lingered long after other areas had recovered. From a modern perspective, this prolonged breathlessness carries an unsettling implication. It suggests that once large-scale oxygen loss is established, it is extremely difficult to undo quickly. The ocean does not snap back to health on human timescales. Its recovery is measured in tens of thousands of years or more. Understanding how long the ocean stayed breathless helps explain the scale of its transformation. It was not a temporary deviation from normal conditions. It was a sustained state that reshaped ecosystems, altered evolutionary trajectories, and left lasting marks in the geological record. As this story continues, attention turns toward what happened when breath finally began to return. Recovery was not smooth or uniform. It came unevenly, with setbacks and delays, and it produced an ocean that was not simply restored, but changed. To understand that process, we need to follow the slow, uneven path by which oxygen re-entered the system, and life cautiously rebuilt itself in waters that had been hostile for an unimaginably long time. Recovery, when it finally began, did not arrive as relief. There was no sudden turning point where the ocean shifted cleanly from breathless to healthy. Instead, recovery unfolded as a drawn-out, uneven process full of hesitation and reversal. In many ways, it was more fragile than the collapse that preceded it. The system had learned how to exist without oxygen. Learning how to breathe again took far longer. The first changes did not begin in the ocean itself. but above it. Atmospheric conditions slowly shifted as the forces that had driven warming weakened. Volcanic activity declined or moved elsewhere. Carbon dioxide levels began to fall, not because the planet corrected itself intentionally, but because long-running processes finally gained the upper hand. Chemical weathering on land continued to draw carbon from the atmosphere. Organic matter buried in black shales locked carbon away for geological timescales. Bit by bit, the sky became less saturated with heat-trapping gases. As temperatures cooled, the ocean responded cautiously. Cooling did not immediately restore circulation. Stratification had become deeply entrenched. Density differences between surface and deep waters were still insufficient in many regions to drive strong sinking. But cooling shifted probabilities. Seasonal contrasts increased. High-latitude waters began to approach the thresholds needed to sink again. When sinking resumed, it did so unevenly. Some regions recovered earlier than others. Certain basins began to receive small amounts of oxygenated water at depth, while others remained isolated. The deep ocean did not reoxygenate as a single connected system. It reawakened in fragments. These early oxygen intrusions were often brief and limited. Oxygen would enter a layer, react with reduced compounds and disappear. Iron oxidized. Sulfide was consumed. The chemical backlog accumulated during anoxia absorbed much of the incoming oxygen before it could spread. From a biological perspective, these early stages of recovery may have gone largely unnoticed. Conditions remained hostile to most complex life. Only after prolonged oxygen delivery did concentrations begin to rise above critical thresholds. Even then, habitable zones were narrow and unstable. Small changes in circulation could expand or collapse them. Life attempting to recolonize faced a shifting landscape, where success in one interval did not guarantee persistence in the next. Biological recovery mirrored this unevenness. Opportunistic organisms were the first to respond. Species with high reproductive rates and flexible tolerances moved into newly oxygenated spaces. Many of these organisms were descendants of the survivors that had endured anoxia. They were not specialists in rich, stable environments. They were generalists, capable of tolerating fluctuation. More complex ecosystems took much longer to re-establish. Reef systems, for example, require sustained oxygenation, stable chemistry, and relatively clear water. After major anoxic events, reefs often remained absent or sparse for millions of years. When they did reappear, they were frequently built by different organisms than before, reflecting the permanent loss of earlier reef builders. The seafloor also recovered slowly. Burrowing animals, once absent, returned gradually as oxygen penetrated sediments. Their activity helped restore sediment mixing, improving oxygen penetration and nutrient cycling. But this feedback only became effective once oxygen levels were consistently high enough to support their metabolism. Until then, sediments remained layered and chemically reduced. This created a threshold effect. Below a certain level of oxygenation, recovery mechanisms could not operate. Above it, they began to reinforce improvement. The ocean did not climb this threshold smoothly. It lingered below it for long periods, occasionally crossing it briefly before slipping back. Fossil records from recovery intervals often show bursts of diversification followed by setbacks. New species appear, then vanish. Communities assemble, then fragment. This instability reflects an environment still in transition, where the physical framework had not yet stabilized enough to support long-term complexity. Chemical evidence supports this picture. Isotopic signatures fluctuate. Trace metal concentrations rise and fall. Black shale deposition may continue intermittently even as lighter sediments begin to appear. These mixed signals indicate a system oscillating near a tipping point, rather than progressing steadily toward full recovery. Another factor slowing recovery was geography. Continental positions and ocean basin shapes did not change quickly. Circulation pathways that had been disrupted remained constrained. Some regions remained poorly ventilated long after others improved. These persistent dead zones acted as sources of reduced chemicals, influencing surrounding waters and slowing broader recovery. In this context, recovery was not simply the reversal of collapse. It was a negotiation between competing processes. Cooling favoured oxygenation. Residual warmth favoured stratification. Buried carbon reduced atmospheric carbon dioxide. Reduced sediments consumed oxygen. Each gain was countered by resistance from the system's own history. Life responded accordingly. Evolutionary innovation continued, but within limits. New forms emerged, often filling roles left vacant by extinct lineages. But these new ecosystems were not replicas of the old ones. They were shaped by the conditions of recovery, not the conditions that existed before collapse. This distinction matters. Recovery did not restore the ocean to a previous state. It produced a different ocean, one that carried the imprint of what it had endured. Diversity increased again, but composition shifted. Food webs lengthened, but along new lines. The memory of anoxia was embedded in the structure of the recovered system. Over very long timescales, as circulation strengthened and oxygen delivery became more reliable, the ocean regained much of its complexity. But this process unfolded over millions of years. From the perspective of any individual species, recovery was effectively permanent change. The uneven road to recovery also highlights how sensitive the ocean is to thresholds. It is easier to destabilize than to rebuild. Collapse can be driven by incremental pressure. Recovery requires sustained favorable conditions over far longer periods. This asymmetry is one of the most important lessons of ancient anoxic events. It suggests that systems built over long periods of stability do not rebound quickly when that stability is lost. They reorganize, and that reorganization carries lasting consequences. As recovery progressed, the ocean began to resemble something recognizably alive again, with expanding habitable zones and increasingly complex interactions. But the shadow of anoxia lingered, shaping which organisms dominated and which never returned. From here, the story naturally turns toward the present, because while ancient oceans eventually recovered, traces of similar processes can be found today, not on the same scale, not yet, but in patterns that echo the past closely enough to warrant attention. The modern ocean is not an anoxic ocean. Oxygen still circulates through most of its depths. Complex ecosystems still exist. Large animals still move through open water and across sea floors. By every everyday measure, the sea is alive. And yet, when scientists study the ocean closely, they find patterns that feel uncomfortably familiar. Not replicas of ancient anoxic events, but echoes. Subtle, localized, and growing signals that resemble the early stages of processes that once pushed the ocean toward breathlessness. One of the clearest of these echoes is the presence of oxygen minimum zones. These are regions typically found at intermediate depths, where oxygen concentrations are naturally low. They form where high biological productivity at the surface leads to large amounts of organic matter sinking and decomposing below, while circulation remains weak. Oxygen minimum zones are not new. They have existed for millions of years, but their size, intensity, and behavior are changing. In recent decades, measurements show that oxygen minimum zones are expanding. In some regions, they are growing vertically, squeezing oxygenated layers into thinner bands near the surface. In others, they are spreading laterally, covering larger geographic areas. The causes are not mysterious. Surface warming strengthens stratification. Warmer water holds less oxygen. Increased nutrient input boosts productivity and decomposition. The same drivers that operated in ancient oceans are at work again, though on a smaller scale. This expansion has real biological consequences. Species that once lived comfortably at certain depths are forced to move. Fish avoid low oxygen layers, altering migration routes and concentrating in narrower zones. This increases competition and changes predator-prey interactions. Some species cannot move quickly enough or far enough and suffer population declines. Invertebrates on the sea floor are particularly vulnerable. As oxygen levels fall, burrowing activity decreases. Sediments become less mixed. Chemical conditions shift. These changes mirror in miniature the early stages of the benthic collapse seen during ancient anoxic events. The feedbacks are familiar. Less biological mixing leads to poorer oxygen penetration, which further degrades habitat quality. Coastal dead zones provide another echo. These regions, often found near river mouths and heavily populated coastlines, experience seasonal or persistent hypoxia driven by nutrient runoff from agriculture and urban areas. Algal blooms flourish, then collapse. Decomposition consumes oxygen. Fish and invertebrates flee or die. Dead zones are not the same as global anoxia. They are localized, often reversible, and influenced by direct human management. But they demonstrate how quickly oxygen loss can occur when nutrient input and stratification align. They also show how difficult recovery can be if underlying drivers remain unchanged. In some cases, dead zones have persisted or worsened despite mitigation efforts. This persistence highlights the same asymmetry seen in ancient oceans. It is easier to create hypoxia than to eliminate it. Once established, low oxygen conditions can resist improvement through sediment feedbacks and altered biological communities. The open ocean shows subtler changes. Long-term monitoring indicates a gradual decline in overall oxygen content in many regions. This decline is small when expressed as a percentage, but significant in absolute terms. Even minor reductions can push marginal systems past critical thresholds. What makes these changes particularly concerning is their consistency with expectations from warming-driven stratification. Climate models predict continued ocean warming, especially in surface layers. This warming is expected to further strengthen stratification, reducing ventilation of the deep ocean. While the modern circulation system is robust compared to ancient configurations, it is not immune to sustained pressure. Another echo lies in nutrient dynamics. Human activity has dramatically altered the global nitrogen and phosphorus cycles. Fertilizer use, fossil fuel combustion, and land use changes have increased nutrient delivery to rivers and coastal waters. These nutrients do not remain confined to shorelines. They eventually reach the open ocean, influencing productivity far from land. This enrichment can enhance carbon export to depth, increasing oxygen consumption below. In isolation, the ocean can absorb some of this additional load, but combined with warming and stratification, it contributes to the same imbalance seen in the past. Chemical signatures also reflect changing conditions. In some oxygen-poor regions, elevated levels of nitrous oxide and methane have been detected. These gases are produced by anaerobic microbial processes and can escape into the atmosphere, acting as greenhouse gases themselves. This creates a feedback loop linking ocean oxygen loss to climate. The modern ocean's chemistry has not crossed into widespread sulfide production in the open ocean. Hydrogen sulfide remains confined to highly restricted environments, but its presence in certain coastal basins and deep isolated waters serves as a reminder of what becomes possible when oxygen disappears entirely. Another parallel lies in biological simplification. In oxygen-stressed regions, food webs shorten. Microbial processes become more dominant. Diversity declines. These changes are localized, but they demonstrate how quickly ecosystems reorganize when oxygen becomes scarce. It is important to emphasize that the modern ocean is not on the brink of a global anoxic event in the same way ancient oceans were. Continental positions, circulation patterns, and baseline oxygen levels are different. The scale of ancient events required sustained forcing over very long periods. That said, the processes themselves are not fundamentally different. They are expressions of the same physical and chemical principles. What the echoes tell us is not that history is repeating exactly, but that the ocean responds predictably to certain combinations of stress. Warm it, stratify it, feed it excess nutrients, restrict its circulation, oxygen declines, biology simplifies. Recovery becomes harder the longer these conditions persist. The timescales differ, but the direction of change aligns. One of the most striking lessons from ancient anoxic events is how long their effects lasted compared to the forces that triggered them. Modern climate change is rapid by geological standards. The ocean's response will unfold over decades to centuries, but some consequences may persist far longer. Oxygen loss initiated now could shape ecosystems for generations. This long memory is easy to overlook because human attention spans are short. Fisheries decline, dead zones expand, individual species suffer. These are often treated as isolated problems. The deeper pattern, linking them to fundamental changes in ocean physics and chemistry, can be harder to grasp. Ancient anoxic events provide context. They show that oxygen loss is not just an ecological issue, but a structural one. It alters how the ocean functions at a basic level. Once altered, the system resists quick fixes. This does not mean the future is predetermined. The ancient record shows both collapse and recovery, but recovery required sustained changes in the drivers of anoxia: cooling, reduced nutrient input, strengthened circulation. These changes did not occur accidentally. They followed from shifts in planetary conditions. In the modern world, some of these drivers are within human influence. Nutrient runoff can be reduced, emissions can be limited, warming can be slowed. These actions do not guarantee stability, but they reduce the likelihood of pushing systems past critical thresholds. The echoes of anoxia in today's ocean are therefore not prophecies. They are warnings written in gradients rather than cliffs. They suggest directions, not certainties. They remind us that the ocean has modes of operation that are very different from the one we rely on, and that transitions between modes can be difficult to reverse. As this story continues, the focus shifts from observation to implication. Ancient anoxic events were not just historical curiosities. They carried lessons about sensitivity, thresholds, and long-term consequences. The question is not whether the ocean can survive change. It always does in some form. The question is what kind of ocean will persist, and what kinds of life it will be able to support. Those questions lead naturally toward the warnings embedded in the ancient record, because while the ocean has endured suffocation before, it did so at enormous cost, and the patterns left behind are not subtle if one knows how to read them. When scientists first began using the term dead zone, it was meant as a practical description, not a dramatic one. It referred to areas of the ocean where oxygen levels drop so low that most animals cannot survive. Fish leave. Crabs crawl out of the water if they can. What remains is a space that still looks like ocean, still moves like ocean, but no longer functions as one in the way we expect. Over time, the phrase took on a heavier meaning, because the pattern it described began to appear again and again, in different places, under different circumstances, yet driven by the same underlying mechanics. Modern dead zones are most visible along coastlines, river mouths, semi-enclosed seas, areas where human activity concentrates nutrients and alters water flow. These zones can form quickly, sometimes within a single season. Excess nutrients fuel algal blooms. The algae die. Decomposition consumes oxygen. Stratification prevents replenishment. Oxygen drops. Life retreats. The sequence is now well documented. What is less obvious, but more important, is how closely this sequence resembles the early stages of ancient anoxic events. The scale is different. The time scale is compressed. The causes include direct human input rather than deep geological processes, but the structure of the problem is familiar. Productivity increases faster than oxygen delivery. Circulation weakens. Consumption outpaces supply. A threshold is crossed, and the system reorganizes. In many coastal dead zones, the reorganization follows a predictable path. Large animals disappear first. Fish and mobile invertebrates leave if possible. Sessile organisms die in place, benthic communities collapse, microbial activity increases, chemical gradients sharpen, the seafloor becomes darker, more reduced, and less biologically mixed. Over repeated cycles, these changes can become semi-permanent. Even if oxygen returns seasonally, the biological community may not fully recover. Species composition shifts toward those tolerant of low oxygen. Burrowing activity remains reduced. Sediments continue to trap organic matter. The system remembers its stress. This idea of memory is central. Dead zones are not just temporary absences of oxygen, they are altered states. Each episode leaves behind conditions that make the next episode easier to trigger and harder to reverse. Sediments enriched in organic material consume oxygen more rapidly. Reduced compounds accumulate. The biological community adapts to scarcity rather than abundance. In this way, modern dead zones mirror the slow creep described in ancient oceans, just on a smaller canvas. Beyond coastal regions, silent depths exist in the open ocean as well. Oxygen minimum zones, already discussed, are expanding and intensifying. In these regions, life does not vanish entirely, but it thins. Vertical habitats compress. The usable depth range for many species shrinks. Animals crowd into narrow bands where oxygen remains just high enough to sustain them. This compression creates its own problems. Predation intensifies, competition increases, reproductive success declines. The system becomes less forgiving. A small additional drop in oxygen can have outsized effects, pushing populations past physiological limits. These silent depths are not dramatic in appearance. There are no obvious surface signals. Satellites cannot easily detect them. Ships passing overhead see blue water and rolling waves. The silence exists below, in layers where interactions have been stripped down to the minimum required for persistence. In ancient oceans, this silence spread over enormous areas. Today, it is patchy. But patchiness does not imply safety. It implies vulnerability. It means that large portions of the ocean are operating close to thresholds beyond which change accelerates. One familiar pattern shared by ancient anoxia and modern dead zones is the mismatch between surface productivity and deep habitability. At the surface, nutrient enrichment and warming can produce bursts of life, blooms, high chlorophyll, apparent abundance. Beneath that abundance lies depletion. This vertical disconnect is misleading. It encourages the perception that the system is healthy because productivity is high. In reality, it signals imbalance. The ocean is producing more organic matter than it can safely process given its circulation and oxygen supply. Another familiar pattern is asymmetry. Oxygen loss happens faster than oxygen recovery. Creating a dead zone can take months. Eliminating one can take years or decades, even when nutrient input is reduced. This lag reflects the same mechanisms that prolonged ancient anoxic events: sediment oxygen demand, chemical backlogs, altered biological communities. In some modern systems, recovery has stalled entirely. Despite reductions in nutrient input, oxygen levels remain low. The system has crossed a line where internal feedbacks dominate over external management. This does not mean recovery is impossible, but it does mean it is no longer straightforward. These patterns are not limited to coastal waters. Enclosed and semi-enclosed seas show similar behaviour. Limited circulation makes them sensitive to warming and nutrient enrichment. Once oxygen declines, renewal is slow. The Baltic Sea, for example, has experienced expanding hypoxic zones despite mitigation efforts. Its deep waters are poorly ventilated. Stratification is strong. Organic rich sediments consume oxygen efficiently. The system behaves in ways that would be recognizable to someone studying ancient restricted basins. The repetition of these patterns across time and space is not coincidence. It reflects fundamental properties of the ocean. Water stratifies when warmed. Oxygen dissolves less readily at higher temperatures. Decomposition consumes oxygen. Circulation controls distribution. These rules do not change. What changes is the scale at which they operate. Ancient anoxic events played out over millions of years in entire ocean basins. Modern dead zones play out over seasons and coastlines. But the underlying dynamics are the same. Both involve pushing the system beyond its capacity to maintain oxygen balance. This continuity challenges the idea that ancient events were exotic or irrelevant. They were extreme expressions of ordinary processes, the same processes that operate today, just amplified and sustained. Another familiar pattern is the role of thresholds. In many modern systems, oxygen levels decline gradually until they reach a point where biological collapse accelerates. Below this threshold, even small additional stress causes disproportionate damage. Above it, the system appears relatively stable. Ancient anoxic events cross these thresholds at a global scale. Modern systems flirt with them locally. The difference is not qualitative, it is quantitative. Understanding this helps explain why dead zones are so difficult to manage. Efforts often focus on symptoms rather than structure. Oxygen is measured, nutrients are regulated, but circulation patterns, sediment chemistry, and long-term warming trends continue to exert pressure. Without addressing these deeper drivers, improvements remain fragile. Silent depths also reveal something about resilience. Systems that have never experienced severe oxygen stress respond differently than those with a history of hypoxia. In the latter, communities are already simplified. Tolerant species dominate. Recovery potential is limited. This echoes the post-anoxic oceans of the past, where complexity returned slowly and unevenly. There is also a psychological dimension to these patterns. Dead zones are often treated as isolated problems, a bay here, a shelf region there. Each is studied, managed, and discussed separately. The broader pattern, linking them through shared mechanisms, can be overlooked. Ancient anoxic events remind us that these are not isolated failures. They are expressions of systemic stress. When enough local failures accumulate, they can merge into regional or even global transformations. This does not mean such a transformation is inevitable. The modern ocean still benefits from strong global circulation, cold polar waters, and relatively high baseline oxygen levels, but it does mean that the direction of change matters. Each expansion of a dead zone, each intensification of an oxygen minimum zone, nudges the system toward a less resilient state. The familiarity of these patterns is unsettling, precisely because it removes the comfort of novelty. There is no mystery here. The ocean has done this before. The rules are known. The outcomes are recorded in stone. What remains uncertain is how far modern systems will be pushed and how long those pressures will persist. Ancient anoxic events required sustained forcing over long periods. Modern forcing is rapid, but whether it will be sustained is a question that remains open. As we move forward in this story, the focus shifts from patterns to warnings. Ancient oceans did not just record what happened, they encoded lessons about thresholds, persistence, and the cost of ignoring slow-moving change. The next step is to look more closely at what those lessons are and what they suggest about the choices that shape the ocean's future, even as its depths grow quieter in ways that feel increasingly familiar. Ancient seas do not warn in the way alarms do. They do not flash or shout or demand attention at a specific moment. Their warnings are quieter, embedded in patterns that only become obvious when viewed across immense spans of time. They speak through repetition, through the fact that the same processes, when pushed in similar ways, tend to produce similar outcomes. What they offer is not prophecy, but precedent. One of the clearest warnings is that large, complex systems can change state without dramatic triggers. There was no single moment when ancient oceans failed. No singular disaster that can be isolated and blamed. Instead, there was accumulation, gradual warming, slowly increasing nutrient loads, subtle weakening of circulation. Each change alone was survivable. Together, sustained over time, they reshaped the system into something far less hospitable. This challenges a common assumption about environmental collapse. the idea that danger announces itself clearly and early. In the case of anoxic events, the most damaging phase came long after the initial pressures began. By the time oxygen loss was widespread and unmistakable, the processes driving it were deeply entrenched. Reversal was no longer simple. Another warning lies in how thresholds behave. Ancient oceans tolerated stress up to a point. Beyond that point, change accelerated. Oxygen levels did not decline linearly. They hovered, fluctuated, and then fell sharply once key feedbacks took over. This non-linearity is uncomfortable because it undermines gradualism as a safeguard. Small additional changes can have outsized effects once thresholds are crossed. The fossil and chemical records show that ecosystems did not adapt smoothly across these thresholds. They fractured. Some components collapsed quickly, others lingered in diminished forms. This system did not reorganize into a new stable state overnight. It entered prolonged instability, marked by repeated failed recoveries. This instability is itself a warning. It suggests that the most disruptive phase of change may not be the initial decline, but the long period of adjustment that follows. During this time, conditions fluctuate unpredictably. Habitats expand and contract. Species attempt to recolonize and fail. Chemical conditions swing back and forth. From a human perspective, this kind of instability would be far more challenging than a single discrete shift. Ancient seas also warn about asymmetry. It took a long time to push the ocean into an anoxic state, but once there, it resisted recovery. The processes that removed oxygen were easier to sustain than the processes required to restore it. Cooling, circulation, and chemical rebalancing had to operate together and persist for long periods before oxygen could return reliably. This asymmetry means that preventing collapse is far easier than repairing it. Once feedbacks favour oxygen loss, the system does much of the work itself. Human effort, had it existed then, would not have been able to reverse conditions quickly. The ocean's inertia would have overwhelmed short-term interventions. There is also a warning embedded in the biological response. Life did not simply rebound when conditions improved. Many lineages were lost permanently, ecosystems reassembled with different players, different structures, and different vulnerabilities. Even when diversity increased again, it did so along altered pathways. This has implications for how loss is understood. Recovery does not mean restoration, it means replacement. What comes back is not what was lost, but something shaped by the constraints of survival. In ancient oceans, this meant simpler systems persisted for long periods even after oxygen returned. Complexity took time to rebuild, and some forms never reappeared at all. Ancient seas also demonstrate that surface appearances can be misleading. High productivity did not signal health. In fact, it often preceded collapse. Algal blooms flourished in nutrient-rich stratified waters, while deeper layers suffocated. From above, the ocean looked busy. Below, it was failing. This disconnect between surface vitality and deep viability is one of the most dangerous patterns to ignore. It suggests that indicators focused solely on productivity can give false reassurance. True stability depends on balance, not abundance. Another warning concerns scale. Anoxic events did not require the entire ocean to be affected at once. They grew from regional problems into global ones as stressed areas expanded and merged. Local failures accumulated until they were no longer local. This pattern undermines the idea that localized environmental damage can always be isolated or contained. In a connected system like the ocean, boundaries are porous. Circulation links distant regions. Chemical changes propagate. What begins as a confined issue can influence much larger areas over time. Ancient records also highlight the role of duration. Stress sustained over long periods mattered more than peak intensity. The ocean did not respond to brief extremes with collapse. It responded to persistent pressure. This suggests that long-term trends deserve more attention than short-term variability. Fluctuations are normal. Oceans have always experienced them. What mattered in the past was direction and persistence, warming that continued, nutrient input that remained elevated, circulation that stayed weak. These conditions allowed feedbacks to accumulate. The warning here is subtle but important. Stability is not defined by the absence of change, but by the system's ability to absorb change without reorganizing fundamentally. When that ability erodes, even modest additional stress can trigger disproportionate consequences. Ancient seas also remind us that recovery required cooperation between multiple processes. No single change restored oxygen. Cooling alone was insufficient. Reduced nutrient input alone was insufficient. Circulation alone was insufficient. Recovery required alignment. This matters because it implies that addressing one driver in isolation may not be enough to prevent or reverse large-scale change. Systems respond to combinations, not single variables. Managing complexity requires acknowledging that reality. There is a further warning in the timescale mismatch between cause and effect. The forces that triggered anoxic events operated over tens or hundreds of thousands of years. Their consequences lasted just as long, often longer. For any individual organism or any short-lived civilization, these changes would have felt permanent. This mismatch complicates responsibility. The actions that contribute to long-term change may not produce immediate dramatic effects. The damage accumulates quietly. By the time consequences become obvious, the opportunity for easy intervention may have passed. Ancient seas do not tell us that collapse is inevitable. They show that it is possible. They show the conditions under which it occurred before. They show the costs. They also show that the ocean is not infinitely forgiving. It can endure stress, but not without consequence. When pushed beyond its capacity to maintain oxygen balance, it does not simply adapt benignly. It reorganizes in ways that reduce complexity and resilience. Perhaps the most important warning is that these processes are not exotic. They do not require rare or extraordinary circumstances. They arise from ordinary physical and chemical principles acting over time. Warm water stratifies. Oxygen dissolves less readily. Nutrients fuel productivity. Decomposition consumes oxygen. Circulation governs distribution. These are the same rules operating today. Ancient anoxic events demonstrate what happens when those rules align in the wrong direction for long enough. They do not tell us what will happen next. They tell us what can happen, and they leave us with a clear implication. The ocean's stability depends not on any single factor, but on balance maintained across climate, chemistry, biology, and circulation. When that balance erodes, the consequences unfold slowly, quietly, and then persist far longer than the initial causes. As the story moves toward its final stretch, attention shifts from warning to endurance, because even after suffocation, after collapse, after long periods of instability, life did not abandon the ocean. It persisted, adapted, and eventually rebuilt something new. Understanding that persistence and what it required offers a final perspective on what collapse and recovery truly mean in a world governed by deep time and patient systems. After collapse, the ocean did not reset itself. There was no clearing of the slate, no clean boundary between what had failed and what would come next. Instead, life remained, thinned and altered, moving forward not with momentum but with patience. Persistence after anoxic collapse was quiet, almost imperceptible on short timescales, yet it was this persistence that determined the long-term shape of the ocean far more than the collapse itself. In the aftermath of widespread oxygen loss, the ocean existed in a reduced state. Habitable space was limited. Conditions fluctuated. Chemical environments remained hostile in many regions. From the perspective of complex ecosystems, the system was broken. From the perspective of life as a whole, it was simply constrained. Life's persistence began at the smallest scales. Microbial communities, already dominant during anoxic conditions, continued to process energy and matter. They did not wait for recovery. They did not need oxygen to function. Their metabolisms operated continuously, cycling carbon, sulfur, nitrogen and iron through pathways that had existed long before oxygen ever shaped the biosphere. These microbial systems formed the foundation upon which everything else depended. They stabilized chemical conditions, even if those conditions were inhospitable to larger organisms. They regulated nutrient availability. They controlled the pace at which reduced compounds accumulated or were transformed. In a very real sense, they kept the ocean alive when most familiar forms of life could not. As oxygen began to return unevenly, these microbes did not disappear. They adapted. Some retreated to deeper layers or sediments. Others shifted metabolic strategies. Their flexibility allowed them to persist across a wide range of conditions, making them constant companions to the ocean's changing state. Multicellular life re-entered the picture slowly. The first animals to take advantage of improving conditions were not pioneers in the heroic sense. They were opportunists, small, simple organisms capable of tolerating instability. Their presence did not signal recovery in the way we usually imagine it. It signaled occupancy. These early colonizers exploited narrow windows of opportunity. A slight increase in oxygen, a temporary improvement in circulation, a local reduction in sulfide. They moved in, reproduced quickly, and established populations where possible. Many of these populations were short-lived. Conditions shifted again. Habitats disappeared. The process repeated. This stop-start pattern defined much of the post-collapse interval. Progress was not linear. Gains were provisional. Life advanced, retreated, and advanced again. From a geological perspective, this looks like noise. From a biological perspective, it was experimentation under constraint. Over long periods, some of these experiments succeeded. Lineages emerged that could tolerate moderate oxygen levels and variable chemistry. These organisms did not require the stable, richly oxygenated environments that earlier ecosystems had depended on. They were built for uncertainty. This tolerance came with trade-offs. These organisms were often smaller, less specialized. Their ecological roles were broader but less refined. Food webs remained short. Energy flowed through fewer steps. The system functioned, but it lacked the layered complexity of pre-collapse oceans. As oxygen delivery became more reliable in certain regions, these tolerant lineages expanded. They did not wait for ideal conditions. They filled space as it became available. In doing so, they shaped the direction of recovery. The future ocean was not rebuilt by restoring what was lost. It was built by amplifying what could survive the transition. This is one of the most important aspects of life's persistence after collapse. Survival determines the starting point for recovery. Whatever traits allow organisms to endure extreme conditions become the raw material for future ecosystems. Traits that were advantageous under stable, oxygen-rich conditions may never return if their carriers go extinct. Over millions of years, this filtering effect altered the trajectory of marine evolution. New groups rose to prominence, others never reappeared. Ecological roles were redefined. Complexity eventually increased again, but it did so on a new foundation. Persistence was not uniform across environments. Some regions recovered faster than others. Shallow, well-circulated areas often regained oxygen earlier, allowing more rapid recolonization. Deep basins lagged behind. These differences created spatial gradients in recovery, with life advancing unevenly across the seascape. These gradients mattered. Regions that recovered earlier acted as sources of colonists for surrounding areas. They seeded recovery elsewhere. But they also reflected local conditions rather than global ones. This meant that the character of recovery varied from place to place. In some areas, recovery favoured particular strategies. In others, different lineages dominated. The ocean did not return as a single coherent system. It reassembled as a mosaic of ecosystems at different stages of development. Throughout this process, extinction remained part of the story. Persistence did not mean safety. Many lineages that survived the initial collapse still disappeared later, unable to compete or adapt as conditions changed again. Persistence was not a guarantee of long-term success. It was a temporary advantage. This ongoing turnover contributed to a prolonged period of evolutionary flux. Speciation and extinction rates were elevated. Ecosystems remained dynamic and unsettled. Stability, when it returned, was the product of long-term sorting rather than rapid improvement. What is striking about this phase is how little drama it contains in the geological record. There are no sharp boundaries, no obvious markers of triumph. Recovery is written in subtle shifts, slight increases in diversity, gradual changes in sediment mixing, the reappearance of burrows, the slow return of skeletal fossils. These signals tell a story of patience. Life did not rush back. It waited for conditions to permit each step. When those conditions faltered, it paused or retreated. This patience reflects the fundamental difference between biological and human timescales. Life can afford to wait tens of thousands of years for improvement. Species can persist in marginal habitats for long periods, provided they can reproduce and maintain populations. Human systems cannot operate on these timescales, but life can. This does not mean persistence is gentle. It involves loss, competition, and repeated failure. It involves long stretches where diversity remains low and ecosystems are fragile. It involves adaptation under constraint, where many possibilities are closed off permanently. But persistence is real. It is the reason the ocean eventually supported rich ecosystems again. It is the reason that collapse did not mark the end of marine life, only a transformation. Looking back, it becomes clear that collapse and persistence are not opposites. They are phases of the same process. Collapse removes complexity. Persistence maintains continuity. Recovery builds new complexity on what remains. This perspective reframes how we think about resilience. Resilience is not the ability to avoid change. It is the ability to continue in altered form when change occurs. Ancient oceans were resilient in this sense. They did not preserve their original state. They preserved life. The cost of that preservation was time. Immense time, during which ecosystems were simpler, less productive, and less diverse. For the organisms living through those periods, this was the only world they knew. As this long arc of persistence eventually led toward renewed complexity, the ocean began to resemble something closer to what we recognize today. But it was not the same ocean. It carried the imprint of its collapse in the structure of its ecosystems and the composition of its life. Understanding this quiet persistence matters because it tempers both optimism and despair. Collapse did not mean extinction of life, but neither did it mean quick recovery or restoration of what was lost. It meant transformation under constraint. As the story reaches its final stretch, this perspective brings everything into focus. The ancient ocean's near death was not a single moment, but a prolonged redefinition of what life could be. And the lesson it leaves behind is not about catastrophe alone, but about the long, patient continuity of life, even when the world it inhabits becomes profoundly unfamiliar. And so we arrive, not at an ending in the usual sense, but at a place where the motion slows enough to listen. The ocean story does not conclude. It continues, indifferent to where we choose to stop paying attention. What changes is our position within it, whether we are rushing past the surface or lingering long enough to notice the deeper currents moving below. The oldest lesson the ocean offers is not dramatic. It does not come packaged as a warning label or a prophecy. It is quieter than that. It is the lesson of balance maintained through movement, of systems held together not by permanence but by exchange. Oxygen moving downward, nutrients moving upward, heat redistributed, life adapting within narrow margins that only remain open as long as those exchanges continue. When that movement slows, the ocean does not protest. It does not resist loudly. It adjusts. It becomes something else. This is perhaps the most unsettling part of the story. The ocean did not nearly die because it was fragile in the everyday sense. It nearly died because it was patient, because it allowed imbalance to accumulate, because it absorbed pressure until its internal structure shifted into a new state that was stable, but diminished. There was no single failure, no villain, no moment when everything went wrong at once. There was warmth that lingered, nutrients that accumulated, circulation that weakened incrementally, oxygen that declined quietly, life that adapted until adaptation was no longer possible. And then there was persistence. The ocean endured breathlessness not by preserving what it had been, but by continuing in altered form. Microbes carried on, chemical cycles continued, energy still flowed, but through fewer channels. Complexity thinned, diversity narrowed. The sea did not vanish, it changed its rules. Recovery when it came required patience of a different kind, cooling that lasted, circulation that slowly reconnected distant layers, oxygen that crept back not in triumph but in increments, life that rebuilt itself cautiously, shaped by what had survived rather than by what had been lost. Nothing about this process was fast. Nothing about it was clean. From a human perspective, this timescale is almost impossible to hold. Hundreds of thousands of years of breathlessness, millions of years of uneven recovery, ecosystems rising and falling repeatedly before settling into something stable again. These are not chapters in a story we are used to telling. They are conditions. And yet, this is how the planet works. Not through singular events alone, but through sustained trends. Not through instant reversals, but through slow negotiations between physics, chemistry, and life. The ocean's oldest lesson, then, is not simply that change happens. It is that the direction of change matters more than its speed, and persistence matters more than intensity. A brief shock can be absorbed. A long pressure reshapes everything. It also teaches that surface impressions are unreliable. The sea can look productive while failing at depth. It can appear stable while its internal connections weaken. The most important processes are often the least visible ones, unfolding far below where casual observation can reach. Another part of the lesson is humility. Life did not control the outcome of anoxic events. It responded to them. The conditions were set by planetary processes operating far beyond the scale of any organism. Evolution filled the space that remained, but it did not prevent collapse. It adapted after the fact. This does not diminish life's resilience. It clarifies it. Resilience is not invincibility. It is continuity through change. It is persistence without promise of restoration. There is comfort in that, but also caution, because the same rules that governed ancient oceans still apply. Water still stratifies when warmed. Oxygen still dissolves less readily at higher temperatures. Nutrients still fuel productivity that must be balanced by circulation. Decomposition still consumes oxygen. These are not historical curiosities, they are ongoing principles. The difference lies in scale and agency. Ancient anoxic events were driven by volcanic activity, tectonic configurations, and slow shifts in planetary chemistry. Today, some of the pressures acting on the ocean originate from much closer to the surface. Nutrient cycles altered rapidly, greenhouse gases accumulating faster than most natural processes have ever produced them. Warming occurring on timescales far shorter than those life has historically adapted to. This does not mean the ocean is doomed to repeat its past. History does not function that way. It means that the ocean has modes, and some of those modes are less hospitable than others. It means that transitions between modes are not easily reversed once they are underway. Listening to the ocean's oldest lesson requires resisting the temptation to look for sudden catastrophe or immediate collapse. It requires attention to slow shifts, to gradients, to trends that persist long enough to matter. It also requires acknowledging that recovery, if it is needed, will not resemble repair in a mechanical sense. There is no reset button. There is only reorganization, and that reorganization favors what remains. Perhaps the most profound aspect of this lesson is how impersonal it is. The ocean did not nearly die because of malice or error. It responded exactly as its physical and chemical rules dictated. Life responded exactly as its evolutionary constraints allowed. There is no moral embedded in the rock layers, only consequence. And yet, for beings capable of reflection, consequence is enough. To listen to this lesson is not to predict an outcome or assign blame. It is to recognize patterns, to understand that systems as vast as oceans can drift into states that feel stable while being profoundly altered, to accept that prevention is easier than recovery, and that recovery reshapes rather than restores. It is also to recognize continuity. The ocean we know today exists because it has endured collapse before. It carries within it the descendants of survivors that tolerated suffocation, instability, and long recovery. Its current richness is not guaranteed. It is the product of conditions that can change. As you sit here now, wherever you are, the ocean continues its slow movements. Surface waters exchange gases with the air. Deep waters circulate gradually. Oxygen dissolves, moves, and is consumed. Life persists within the margins allowed by these processes. Nothing about this requires urgency in this moment. The lesson is not a call to panic. It is an invitation to awareness. Awareness that the ocean is not static, that its health depends on balances that are easy to disrupt and slow to restore. That silence does not always arrive suddenly, but can spread quietly beneath an apparently lively surface, an awareness that life, while persistent, pays a cost when systems collapse. The cost is time, the cost is lost pathways, the cost is worlds that never return. So if there is something to carry forward from this long, winding story, it is not fear but attentiveness, an understanding that deep systems respond slowly but decisively to sustained pressure, that listening requires patience, and that the oldest lessons are often the least dramatic. The ocean does not ask to be saved. It will continue in one form or another. The question that lingers softly without urgency is what form that continuation will take, and how much of what we recognize will be carried with it. For now, there is nothing left to do but sit with that thought. Let it drift, the way water does, without forcing it toward a conclusion. The ocean story is not finished. It is ongoing. And listening, quietly, is already part of the lesson.